Right now, as you sit here, you are falling. Not down, not up, but through space itself. Our planet is not standing still. It's plunging through the darkness at nearly 30 kilometers every second, falling endlessly around the sun. The sun too is falling, dragged through the galaxy toward an invisible point far away, a gravitational well so massive it bends the motion of hundreds of billions of stars. Every planet, every moon, every galaxy is caught in the same silent descent. We call it orbit. We call it motion, but beneath every path lies the same truth. Everything is falling. Gravity is not just a force that pulls apples from trees. It is the architect of the universe. It sculpts the paths of worlds, bends the flow of time, and decides where galaxies live, where stars are born, and where they die. But why does everything fall? Fall into what if there's no down in space? And how can something fall forever, without ever hitting the ground? To answer that, we have to peel back everything we think we know about gravity, because this isn't just a story about a force. This is the story of the hidden current that drives the entire cosmos, a current we are all caught in, a current we can never escape. The universe doesn't stand still, it falls. When we think of falling, we imagine something simple, a rock slipping from a hand, a leaf drifting to the ground, an apple letting go of its branch. But that's only the smallest piece of a much larger truth. Falling is not just what happens when something goes down, it's what happens when something follows its natural path through space. Right now, you are falling toward the center of the Earth. You don't notice it because the ground pushes back, holding you up. But if that ground were to vanish, you wouldn't suddenly start falling. You'd simply keep doing what you were already doing, without interruption. That is the essence of free fall. Step off a ledge and you don't create a new motion. You just stop resisting the one that was already there. The same thing happens on the grandest scales imaginable. Every astronaut aboard a spacecraft orbiting Earth is falling. Not upward, not downward, just endlessly sideways, missing the planet over and over again. We call this an orbit, but physically it's a fall, a perfect continuous fall that never ends. The craft isn't weightless because gravity is gone. It's weightless because everything inside is falling at the same rate. The walls, the instruments, the astronauts all moving together. That's why when they float, they're not defying gravity. They're obeying it perfectly. Imagine throwing a ball forward. The harder you throw, the farther it travels before hitting the ground. Throw it fast enough, about 28,000 kilometers per hour, and the ground curves away beneath it as quickly as it falls. It never lands. It just keeps falling around the Earth forever. That's what a satellite is. A rock in permanent free fall. This idea is so counterintuitive that it took humanity centuries to understand it. To us, falling has always meant moving down, but in the language of the universe, down doesn't exist. There's only direction, the path curved by gravity. Orbit isn't the opposite of falling. It is falling seen from a wider lens. The same is true for the moon. It's not hanging motionless in the sky. It's plunging toward Earth at every moment. But as it does, Earth curves away beneath it, so the fall becomes a loop, a graceful arc that has lasted for billions of years. That's why we never see it crash. It's always falling, always missing, always returning, and so are we. Every one of us, every city, every ocean. The entire surface of the planet is caught in this endless fall, locked in a dance around the sun that began long before life ever appeared. It's easy to believe the sun is holding us up, but the truth is simpler and stranger. We are falling toward it, and the only reason we don't collide is because we're falling fast enough to keep missing. The universe doesn't need a hand to keep us in place. Gravity doesn't push or pull like some invisible string. It simply sets the stage and motion does the rest. When you float, when you orbit, when you move, you are following the most natural path the universe allows. Every orbit is a fall that never ends. Every world is a stone flung so fast it keeps missing the heart it's falling toward. And every second of your life, whether you feel it or not, You're part of that same silent motion. The apple falls for a few seconds. The moon has been falling for 4.5 billion years, and our planet will keep falling for billions more. For most of human history, falling was something we understood only with our eyes. We saw objects drop to the ground. We felt the pull in our muscles, but we didn't know why. Why does everything seem drawn toward the Earth? And why do the heavens, the sun, the moon, the stars seem to follow different rules entirely? For centuries, people believed they were separate worlds. What happened in the sky belonged to the divine. What happened on the ground was ordinary. Then one quiet idea would erase that boundary forever. Isaac Newton looked at the simplest thing, an apple falling, and saw something universal. The same rule guiding the apple also governed the motion of worlds. Gravity wasn't local, it was everywhere. He realized that the familiar downward pull we feel is not a special isolated effect of Earth, but a universal interaction linking every object to every other object in the cosmos. The apple's fall and the motion of the moon are 2 pages of the same story. One law, one universe. Newton expressed this idea with a breathtakingly simple equation. Every object in the universe attracts every other object, with a force proportional to their masses and inversely proportional to the square of the distance between them. 2 stones, 2 stars, 2 galaxies, it doesn't matter. The rule is the same. This idea changed everything. For the first time in history, the laws that govern the ground and the heavens were unified. The apple falling beside Newton's chair obeyed the same law, as the planets circling the sun and the stars drifting through space. There was no longer a special realm above the clouds. The entire cosmos was connected by the same invisible thread, and this thread wasn't just a poetic idea. It could be measured, calculated, predicted. With it, Newton could compute how far a cannonball would travel if fired fast enough. He could predict the paths of comets, the timing of eclipses, the orbits of planets. He turned falling into mathematics, and mathematics in turn revealed the hidden architecture of the universe. Perhaps the most revolutionary part of Newton's idea was that gravity works both ways. The Earth pulls the apple down, yes, but the apple pulls the Earth upward too, just imperceptibly, because the Earth is so massive. Every object pulls on every other. You are pulling on the distant stars right now, and they are pulling on you. Gravity became more than just a familiar sensation beneath our feet. It became a universal language, spoken quietly between every grain of matter in existence. It decides the shape of planetary systems, the structure of galaxies, the formation of stars. Falling isn't an exception, it's the default. This idea did more than explain how things move. It gave humanity a way to navigate the cosmos. Centuries after Newton's death, his equations still guide spacecraft to distant worlds. We use his laws to sling probes around planets, to land on moons, to aim telescopes at exoplanets orbiting faraway stars. Every maneuver is a silent conversation with gravity. But even Newton's brilliance had its limits. His equations told us what gravity did. They did not tell us what gravity was. Why should 2 objects separated by empty space reach toward each other at all? What was this invisible influence that crossed the void? That question would wait nearly 200 years for a man who would offer an even stranger answer, an answer that would turn the very fabric of space and time inside out. Newton's idea of gravity ruled for centuries. It sent ships across oceans, planets across the sky, and spacecraft to the moon. But it carried a quiet, unsolved riddle. What exactly was this invisible force reaching across empty space? How could the Earth pull on the moon without anything in between? In the early 20th century, one man offered an answer so radical it changed our picture of reality itself. Albert Einstein did not see gravity as a mysterious pull. To him, it was geometry. Imagine space not as a blank, rigid stage, but as a soft fabric that bends when something heavy sits on it. A star, a planet, even your body. Everything with mass pushes down on this fabric. Other objects moving nearby don't feel a force pulling them. They simply follow the curves in that fabric. They fall not because they're being dragged, but because space itself tells them to. This was Einstein's great leap. Gravity isn't a force. It's the shape of space-time. It's hard to overstate how profound this is. The Earth isn't pulling the Moon toward it. The Earth is bending the space-time around it. The Moon is just coasting through that curve following the straightest path available, a geodesic as physicists call it. This is why astronauts in orbit feel weightless. They're not escaping gravity. They're moving along space-time's natural curves. Gravity hasn't disappeared. They've simply stopped fighting it. Even you standing on the ground are trying to follow that curve, but the floor pushes back, holding you in place, preventing you from falling along your natural trajectory. What we call weight is not gravity pushing down, it's the ground pushing up. Resisting the full space-time is urging us to take, and here's the most astonishing part. Mass doesn't just bend space, it bends time too. Near a massive object, clocks tick more slowly. Every fall is not just a movement through space, it's a slide through time. This is why Einstein's theory doesn't just describe falling, it reveals its true nature. When an object falls toward a planet, a star, or a black hole, it's not being yanked downward. It's simply doing what it would always do in curved space-time. Follow the easiest path. This is why two satellites in orbit don't need engines to keep moving. They glide effortlessly along those curves. This is why planets stay in orbit for billions of years without slowing down. And this is why even light, the fastest thing in the universe, can be bent by gravity. It isn't that gravity reaches up and grabs it. The light is just following a straight line through a curved universe. The beauty of this idea is its simplicity. Einstein replaced an invisible force with something deeper, a kind of cosmic landscape. Objects don't tell each other how to move. They tell space-time how to bend, and space-time tells them how to move. This is why falling is universal. A feather, a hammer, a star, a beam of light. They all fall along the same curves, because they all live in the same geometry. When Einstein first proposed this, it sounded impossible to prove. But in 1919, during a total solar eclipse, light from distant stars was observed bending around the sun. The stars hadn't moved, space-time had. And humanity saw for the first time gravity not as a pull, but as a shape. It's a strange realization. Falling is not something happening to you, it's the universe itself gently guiding your path through its curved stage. You're not being dragged. You're following the map written into the fabric of reality. And once you understand that, the question changes, not why do things fall, but what is the shape of the fall? Because in Einstein's universe, the shape of space-time decides everything. It determines how stars move, how galaxies form, and ultimately, how time flows. Every fall is a journey through space, but more quietly and far more profoundly, it's also a journey through time. Near Earth's surface, you don't notice it. Seconds feel the same, clock seems steady. The fall of a stone looks like nothing more than acceleration, but the universe measures time differently from us. Where gravity is stronger, time itself slows down. If you place two clocks, one on a mountain peak and one at sea level, they won't agree after a while. The lower clock, deeper in Earth's gravitational well, will tick a little slower, not because the gears turn differently, but because time itself is flowing at a different rate. This is not an illusion, it's measurable. Gravitational time dilation is one of the most precisely confirmed predictions of general relativity. GPS satellites have to correct for it every second. Without those tiny corrections, just microseconds each day, your navigation would drift kilometers off course in a matter of hours. What's remarkable is why it happens. Einstein's curved space-time isn't just a stage for falling, it's a clock. The closer you get to a massive object, the deeper you fall into its well, and the slower time runs relative to the universe around you. Falling isn't just a change in position, it's a shift in the tempo of existence. Now imagine falling towards something more massive than Earth, a neutron star, a black hole. The difference becomes extraordinary. For an outside observer, someone falling toward a black hole seems to slow down, their movement stretching their clock, crawling to a halt at the event horizon. From their own perspective, nothing strange happens. They fall freely, crossing the boundary in moments, but to the rest of the universe their time has almost stopped. Falling in this extreme sense is not just movement through curved space, it's movement through a warped river of time. The closer you are to a massive object, the steeper that river becomes, and at the edge of a black hole it becomes a waterfall. Time doesn't just slow, it plunges. Even Earth participates in this cosmic effect. When astronauts orbit above us, they're not just floating. Their clocks are ticking ever so slightly faster than ours. The difference is tiny, but it accumulates. After 6 months in orbit, an astronaut is a fraction of a second younger than they would be on the ground. Falling shapes time gently for us, violently for stars. This means every fall, whether it's an apple dropping or a star spiraling toward a black hole, is also a time shift. Every object in the universe experiences time at its own rhythm, set by the depth of the gravitational well it's falling through. Even light is affected. A photon climbing out of a gravitational well loses energy, its wavelength stretching, its colour shifting to red. A cosmic signature of time running differently at its origin. This is what makes gravity so unlike any other interaction. It doesn't just decide where things move, it decides how they experience time. Where there is no mass, time flows straight and uniform. Where there is mass, it curves, slows, twists. Falling is how matter moves through that landscape, a movement written into time itself. So the next time you watch something fall, remember that beneath the motion you see, there's another motion you don't, adrift through the hidden contours of time. If you throw a stone, it arcs through the air and falls to the ground. Throw it harder and it travels farther, but if you could throw it fast enough, something strange would happen. It would keep missing the ground. Not because gravity stopped, but because the curve of the Earth dropped away beneath it as quickly as it fell. That stone would never land. It would circle the planet forever. Now imagine scaling this up by a few orders of magnitude. Replace the stone with Earth. Replace the ground with the sun. This is what it means to orbit a star. It's not floating, it's falling perfectly sideways. The Earth is plunging toward the sun at every moment. If it were standing still, it would crash into the solar furnace in just a few months. But it isn't standing still. It's moving forward at about 30 kilometers per second. That forward motion bends into a loop, an endless path where our planet keeps falling, and the sun keeps missing. This delicate balance between gravitational pull and lateral motion is what makes orbits possible. Too slow and Earth would spiral inward, vanishing into the sun. Too fast and it would escape altogether, flung into the darkness of interstellar space. We exist in the razor-thin middle ground where falling and motion are perfectly matched. What makes this remarkable is that nothing is holding Earth up. There are no invisible strings, no force counteracting gravity. Orbit isn't a battle between two opposing powers. It's a harmony between motion and geometry. Earth isn't resisting the sun, it's obeying it. And this dance isn't unique to our planet. Every object in the solar system is caught in the same falling loop. Mercury, close to the sun, races at nearly 48 kilometers per second, falling along a tight curve. The distant Neptune drifts slowly, its orbit wide and long. Comets plunge in from the frozen edge of the system, whipping around the sun in wild, graceful arcs. Each one is simply falling with a different rhythm. These orbits aren't static. They process wobble and shift over time. Gravity is patient but relentless, tugging every world along its curved path. The result is a cosmic clockwork that has endured for billions of years. For us, this perfect orbit is more than just a path through space. It's the reason we have seasons, the reason temperatures remain stable, the reason life has time to emerge and evolve. If Earth's orbit tilted too wildly or drifted too far, our world would freeze or burn. We survive not because gravity is gentle, but because motion and gravity have found a fragile, exquisite balance. This is the quiet truth behind our orbit. We're not standing in space looking at the sun. We are falling around it, endlessly, silently, caught in a precise gravitational embrace that decides everything about our world, from the length of a year to the fate of every living thing that's ever existed. Every orbit has a beginning, every star, every planet, every moon. Before they could fall around something, they first had to fall into something. Long before Earth was a blue marble circling the sun, there was only a cold, dark cloud of gas and dust, silent, vast. For millions of years it drifted through space weightless in appearance. But inside that cloud, gravity was always at work. Every atom, every grain of dust was pulling on every other, whispering the same universal language Newton described. Over time, those whispers became a chorus, and the cloud began to collapse. The process was slow at first. Tiny fluctuations in density, perhaps born from ancient shock waves or quantum ripples, gave gravity a foothold. Wherever the cloud was slightly denser, gravity grew stronger, pulling in more material, making it denser still. A runaway fall had begun. As the cloud collapsed inward, it didn't just shrink. It spun faster and flattened into a disk. This is a fundamental property of falling matter. When it loses height, it gains speed. When it collapses, it organizes. At the center of this swirling disk, pressure built up. Temperature climbed. Atoms slammed together with such violence that fusion ignited, and a star was born. Our sun is the product of that ancient fall. It wasn't placed at the center. It emerged there forged by the weight of gravity, crushing a cloud into light. Around it, leftover gas and dust kept falling, colliding, sticking together. Tiny grains became pebbles. Pebbles became boulders. Boulders became worlds. This is how planets are made, not from chaos, but from collapse. Gravity doesn't just pull things down. It sculpts them. It turns drifting dust into structured systems. Each planet is the frozen memory of that first colossal fall, but the collapse never really stops. Even now, the sun is still pulling on everything around it. The planets are still locked in their endless arcs. Comets still dive inward from the frozen edge of the solar system, like ancient messengers carrying the memory of the cloud we came from. What's remarkable is how gravity does all this without effort. There is no blueprint, no hidden hand arranging the planets. Just matter and the simple rule that everything attracts everything else. Given enough time, falling builds stars. Falling builds planets. Falling builds entire solar systems. The orbit of Earth today is just the aftermath of that great collapse. Every sunrise, every passing season, every heartbeat of this planet is part of a story that began when a cloud of hydrogen decided to fall. There's a quiet truth about every star. Its life is a battle against falling. A star is born when gravity crushes a cloud of gas until fusion ignites. And from that moment on, it lives by pushing back. The furious heat from fusion swells outward, countering the relentless inward pull of gravity. For millions or billions of years, this cosmic tug-of-war holds the star in balance. But no fire burns forever. When the fuel runs out, the star's light falters, its outward pressure fades, and gravity doesn't, without anything left to resist it. The star begins to collapse inward. At first, this fall can be gentle, a red giant shedding its outer layers, leaving behind a dense ember. But if the star is massive enough, the collapse doesn't stop. It accelerates. The core is squeezed to unimaginable densities. Atoms are stripped apart. Protons and electrons fuse into neutrons. If even that isn't enough, the collapse punches through every known form of matter, crushing it past the point of no return. Space itself caves in. A singularity is born. A black hole is not an object in the usual sense. It's a region of space-time where the fall becomes absolute. There is no ground, no stable orbit. Inside this invisible boundary, the event horizon, every path leads inward. Even light, the fastest thing in the universe, cannot escape the fall. From the outside, a black hole looks deceptively calm. Empty space, nothing to see. But near its edge, the laws of physics begin to twist. Time stretches, distances warp. A falling object slows from our point of view, its image frozen and red-shifted into darkness. But to the object itself, nothing special happens. It crosses the horizon without fanfare, and continues falling forever. This is gravity at its most extreme, a place where the inward pull is no longer something you can fight, or even balance with motion. There is no sideways path to escape, no velocity fast enough to miss the center. Once you cross that line, the fall isn't optional. It's geometry. These cosmic abysses are scattered throughout the universe. Some are the corpses of dead stars. Others are supermassive millions or billions of times heavier than the Sun, lurking at the hearts of galaxies. Even our own Milky Way is anchored by one, a silent gravitational engine that shapes the galaxy around it. And here lies the ultimate truth of falling. When gravity wins completely, when no force can hold anything up, falling doesn't end with a crash. It becomes a destination, a one-way journey into a place where space-time itself collapses. Black holes are not monsters in the dark. They are the purest expression of gravity's power, the final chapter of what happens when falling has nowhere left to go. For a long time we thought galaxies floated like islands in a calm sea of space, majestic, isolated, still. But the universe has never been still. Every star falls, every planet falls, and entire galaxies fall too. Our own Milky Way is not resting in some cosmic void. It's plunging through the fabric of space-time. At hundreds of kilometers per second, our galaxy, together with its neighbors, is being pulled towards something vast, something hidden. A gravitational center so immense it bends the flow of hundreds of billions of stars. Astronomers call it the Great Attractor. We can't see it directly. It's shrouded behind dense walls of dust and light, masked by the plane of our own galaxy. But we can feel its pull. Every galaxy in our cosmic neighborhood is drifting toward it, drawn by an invisible hand. This is not orbit. This is not collapse in the usual sense. This is falling on a scale so large that it stretches across hundreds of millions of light years. Imagine an ocean current, so slow you cannot feel it, but so powerful it carries entire continents. The Great Attractor is that current, a gravitational river flowing through the cosmic web. We, along with thousands of galaxies, are caught in this silent drift. We're moving through space at more than 600 kilometers per second. We don't feel it because everything around us, the sun, the planets, the stars, is moving too. Like a leaf carried downstream, we're part of the flow. And the Great Attractor isn't alone. Far beyond it lies Laniakea Supercluster, a titanic basin of gravity so large it defines an entire region of the observable universe. It's not a structure we orbit. It's a gravitational landscape, and we are sliding down its slopes. This is the hidden architecture of cosmic motion. Galaxies don't just expand away from each other because of cosmic expansion. They also fall together, gathering into clusters, clusters into superclusters, forming an intricate web of flows converging on massive attractors. Every filament, every node, every cluster is shaped by billions of years of falling. Even on these colossal scales, gravity is patient. The journey of our galaxy toward the Great Attractor will take billions of years. We may never reach it. The accelerating expansion of the universe may stretch the fabric of space faster than we can fall. But the pull is there, a faint but relentless tug that guides the great migration of galaxies. It's strange to think about. The stars overhead, the familiar constellations, the solar system itself. None of it is fixed. We're all passengers on a galaxy that's falling towards something vast and unseen. Not a cliff, not a pit, but a gravitational basin woven into the structure of the cosmos itself. Falling doesn't end with planets or stars or black holes. It stretches across the entire universe, guiding rivers of galaxies through the darkness. Every orbit, every collapse, every drift, all of it is part of a single cosmic current, and we are riding it. When astronomers measured how far stars orbit around their galaxies, they expected something simple. Closer stars should move quickly. Distant stars far from the centre should move slower, just like planets in our solar system. That's what Newton's laws predict. That's what logic demands. But when they looked, they found something impossible. Stars at the edges of galaxies were moving too fast. Far too fast. At those speeds, they should have flown off into the void long ago, spiralling away like stones flung from a sling. And yet, they stayed. The galaxies held together. Something unseen was pulling them in. This was the first great clue to one of the universe's deepest mysteries. Dark matter, an invisible substance that does not shine, does not reflect, does not absorb light at all, but it has mass, and mass means gravity, and gravity means falling. Every galaxy is wrapped in a vast halo of this unseen matter. It extends far beyond the visible disk, creating a gravitational well much deeper than what we can see. The stars aren't orbiting an empty space. They are falling through a hidden landscape. It's almost like watching leaves swirl in a wind we can't feel. We see the motion fast, smooth, impossible, and from that motion we infer the invisible force shaping it. Dark matter is not some exotic detail on the edge of physics. It is the dominant sculptor of galactic motion. Without it, galaxies would not hold together. Without it, they would tear themselves apart. And this isn't limited to a few galaxies. The entire cosmic web, clusters, superclusters, streams of galaxies, is threaded together by dark matter. It forms a vast skeleton beneath the visible universe. What we see, the stars, the gas, the brilliant spiral arms, is just a thin film of light draped over a colossal invisible structure. When galaxies fall toward one another, they're not just pulled by what we can see, they're sliding down the gravitational basins carved out by dark matter. When clusters merge, dark matter shapes the collision. When stars orbit, it holds their paths steady. Even the motion of our own Milky Way through space is guided by this hidden gravity. We are falling always, not just toward visible stars and galaxies, but toward something we can't see at all. It's a strange realization. The cosmos we observe, the brilliant tapestry of stars, is not the main story. It's the shadow of something larger, heavier, quieter, a gravitational structure that defines where everything falls. We don't yet know what dark matter is made of. It might be unknown particles, or something more exotic entirely, but we know it's real because we can see its fingerprints. In the way the universe moves, gravity is its voice. Falling is its signature. When we look deep into the night sky, we see scattered points of light, galaxies shining like islands in a dark ocean. But if we could step back far enough, if we could see the entire universe as one structure, it wouldn't look random at all. It would look like a web, a vast intricate network of filaments and nodes, billions of light years across. This is the cosmic web, the hidden skeleton of the universe. It is the shape that gravity has drawn. Over 8 billion years of falling. In the beginning, matter was almost perfectly smooth. Tiny quantum fluctuations, amplified during the early expansion, gave gravity just enough unevenness to work with. Where there was slightly more matter, gravity grew a little stronger. More material flowed in. The well deepened. The fall accelerated. Over time, those tiny ripples became rivers. Galaxies didn't appear everywhere. They formed along these gravitational rivers, streams of matter sliding down into filaments. Where filaments intersected, the fall intensified. clusters formed, superclusters emerged, and eventually the great attractors of the universe took shape. It's a strange kind of architecture. Gravity doesn't build by pushing things into place. It builds by letting them fall, slowly, inevitably. The universe sculpted itself by following the flow of its own gravity. Dark matter is the hidden frame behind this sculpture. It makes up most of the mass. Its gravity guides ordinary matter gas dust stars into the filaments we see today. Every galaxy, every star, every cluster is a drop of light caught in an invisible gravitational river. The vast voids between filaments aren't truly empty. They're simply places where matter has fallen away, where gravity has drawn it elsewhere. The result is a pattern both chaotic and precise, a cosmic network so large that even light takes hundreds of millions of years to cross a single strand. What's remarkable is how similar this structure looks at every scale. Stars fall into galaxies, galaxies fall into clusters, clusters fall into superclusters, and superclusters flow along these colossal filaments, like beads caught in cosmic streams. This is the shape of the universe not as a static map, but as a frozen moment in an endless fall. Every filament is a trace of motion. Every cluster is a place where matter has gathered at the bottom of a gravitational basin. And those basins are still deepening. Even today, the cosmic web isn't finished. Galaxies continue to drift along these filaments, colliding, merging, reshaping the universe as they fall billions of years from now. Many of these rivers will merge into fewer, larger structures as the great gravitational engines continue their silent work. The shape of the cosmos is not a blueprint. It's a memory, a record of where matter has been falling. Since the beginning of time, before galaxies, before stars, before planets, the universe was smooth, not empty, not silent, but astonishingly uniform. In the first few 100,000 years after the Big Bang, matter and radiation were intertwined in a hot, glowing soup. Everywhere you looked, the temperature was almost the same. The density almost perfectly even, but not quite. Hidden in that uniform sea were tiny imperfections, fluctuations as small as 1 part in 100,000. These were the first cracks in the stillness. They weren't galaxies or stars or even atoms bound together. They were ripples, minuscule variations in density seeded by quantum processes and amplified by cosmic inflation. And that's all gravity needed. Where the density was slightly higher, gravity became slightly stronger. Where it was stronger, it pulled in more matter. Where more matter gathered, the pull deepened. It was the beginning of the great cosmic cascade, a chain reaction of falling. Over millions of years, those tiny ripples grew. The universe expanded, but gravity worked patiently, turning gentle hills into valleys, valleys into wells, wells into rivers that would one day become filaments and clusters. The cosmic microwave background radiation we observe today is a fossil of that moment, a map of those first gravitational whispers. When the universe cooled enough for atoms to form, light broke free and streamed across space, but matter pulled by gravity began its slow inward drift. There was no grand explosion forming galaxies, no sudden collapse, just falling everywhere all at once over billions of years. Those tiny overdensities became the cradles of future structures. Some would grow into galaxies, others into clusters, and others into the vast cosmic nodes anchoring entire regions of space. Everything from the orbit of Earth to the path of galaxies across billions of light years was already encoded in those faint ripples. In a way, the universe has never really stopped falling. It's been doing it since the first second. Gravity didn't emerge later to shape what existed. It was there from the beginning, quietly guiding the flow of matter, the moment matter itself came to be. This is one of the most profound truths in cosmology. All the complex motion we see today, the swirling galaxies, the dancing stars, the great migrations of clusters, is just the amplified echo of those first fragile imbalances. Everything began as a whisper. Gravity turned it into a chorus. If you could freeze the universe in that ancient moment and press play again, it would all unfold the same way. The rivers of matter would still slide down the same invisible slopes. The same filaments would form, the same galaxies would rise, the same falls would happen. We are living inside the long tail of that first gentle tumble. Time has a direction. A glass shatters but never reassembles. Smoke disperses but never flows back into the match. Stars burn their fuel but never spontaneously grow younger. This irreversible flow is what we call the arrow of time. And at the heart of it lies something unexpected: gravity. In the earliest moments after the Big Bang, the universe was smooth, extremely smooth, and that smoothness meant something profound. Low entropy, low disorder, a state balanced on a knife's edge. But gravity doesn't like smoothness. A smooth universe is unstable. The tiniest irregularities grow into wells, wells into structures, structures into galaxies and stars. Gravity amplifies imperfection, and as it does, entropy increases. Here's the strange part. Most forces in nature push things toward uniformity. Heat spreads energy, disperses, but gravity works the other way. It creates structure, it clumps matter together, forms stars, planets, clusters, black holes, and in doing so, it drives the universe toward a higher entropy state. When a cloud of gas collapses under gravity, the gas becomes hotter, denser, more chaotic. The outward simplicity of a sphere hides a wild increase in microscopic disorder. This is why stars shine. This is why black holes are born. Every fall, whether it's an apple or a galaxy, is a small step along the arrow of time. This connection runs deep. Without gravity, the universe would simply expand and cool, becoming thinner, colder, emptier, but not more structured. Time would still pass, but it would be quiet, uneventful. Without the irreversible drama of collapsing stars and merging galaxies, with gravity, time acquires texture. Each gravitational fall marks a break in symmetry, an event that cannot be undone without violating the statistical flow of entropy. Once a star forms, once matter clumps, the universe has moved forward, and it won't go back. Even black holes, the ultimate endpoints of gravitational collapse, carry enormous entropy. In fact, the entropy of a single black hole can exceed that of all the stars in a galaxy combined. This means the greatest increase in disorder isn't when things fall apart, but when they fall together. The arrow of time isn't just written in broken glasses or burning stars. It's etched into the way the universe falls. Every collapse, every merger, every orbit slowly decaying is a one-way trip forward. And this is why we remember the past but not the future. The universe began in a low entropy state, and gravity has been guiding it toward higher entropy ever since. Falling is not just motion through space, it is the unfolding of time itself. If the universe had never fallen, time might still exist as a coordinate, but it wouldn't feel like time. No stars, no light, no evolution, no history. It is the act of falling structure forming entropy rising that gives time its direction. The universe falls forward, and so does time. Every heartbeat, every breath, every sunrise is possible. Because the Earth is falling, it's not just a poetic idea. Gravity is the silent architect of everything life depends on. It shapes the star we orbit, it fixes our distance from it, and it holds the thin film of air that keeps us alive. Our planet is trapped in a perfect gravitational dance around the sun. This isn't a coincidence, it's a requirement. Too close and the oceans would boil. Too far and they would freeze solid. We live inside a narrow habitable zone, a fragile balance set by the interplay between sunlight and falling motion. This is why the Earth's orbit matters, because falling along the right curve means receiving the right energy. Gravity also holds our atmosphere in place. Without it, the air would simply drift away into space. Every molecule of oxygen, every drop of water vapor, every layer of protection that shields us from radiation All of it is here because our planet is heavy enough to keep it. Every breath is borrowed from a well of gravity. But the role of falling goes deeper than that. Inside the Earth, gravity squeezes rock and metal, driving convection in the molten core. This motion creates a magnetic field that wraps the planet like a shield, deflecting deadly solar wind and cosmic particles. Without it, the atmosphere would be stripped away, and the surface would be sterile. Gravity also sets the pace of our days and seasons. The tilt of Earth's axis, the shape of its orbit, the pull of the moon, all orchestrated by falling. These cycles regulate temperature, climate, tides, and currents. They create stability, the one thing life needs most to endure. Even the sun itself, the source of all our energy, exists because gravity once collapsed a cloud into a burning star. The warmth you feel on your skin began as a fall billions of years ago. Every living organism is powered by energy released from a cosmic collapse long past, and gravity doesn't just make worlds habitable, it holds them together long enough for life to arise. Stars burn for billions of years because gravity and fusion are locked in balance. Planets orbit steadily, giving evolution time to unfold. Tides driven by the moon's pull may have nurtured the first fragile ecosystems at the edges of ancient seas. Life isn't an interruption in the universe's falling motion. It's a byproduct of it, an emergent pattern shaped by forces that have been at work since the beginning. We are not separate from the fall, we are its consequence. When you stand on the ground and look up at the sky, you're not just seeing stars. You're seeing the infrastructure that makes your existence possible, a planet held together by gravity, bathed in the steady light of a star born from collapse, protected by fields forged deep in its core. Without gravity, there would be no stable orbits, no atmosphere, no oceans, no sun, no life. Falling is not the enemy of life. It's the reason it exists. Gravity doesn't stop at the surface. It reaches deep all the way to the heart of the world. When Earth first formed, it was not the calm blue world we know today. It was a storm of fire and stone. Asteroids collided. Dust gathered. Each impact added more mass. And with more mass came more gravity. This relentless pull crushed the growing planet under its own weight. Heating it from within, that ancient heat never fully went away. Gravity keeps it alive. Deep beneath our feet, the pressure is unimaginable. Iron and nickel are squeezed into a dense core. Temperatures soar higher than the surface of the sun. This is not just leftover warmth, it's gravity at work, converting the energy of countless falls into a furnace beneath our world. Inside that furnace, something extraordinary happens. The molten outer core flows and churns, stirred by heat escaping outward. This movement of charged metal generates Earth's magnetic field, a vast invisible shield that protects the planet from the solar wind. Without this field, our atmosphere would have been stripped away long ago, and life might never have found a foothold. Above the core, in the thick layer of rock called the mantle, gravity drives another kind of motion. Hot material rises, cooler material sinks. This slow, endless, overturning mantle convection is the heartbeat of the planet. It pushes and drags on the crust above, shaping continents, lifting mountains, opening oceans. The continents you stand on are not fixed. They drift, collide, and tear apart over tens of millions of years. Each movement is powered by heat, and that heat is held concentrated and sustained by gravity's squeeze. Volcanoes erupt because mantle plumes rise. Earthquakes shake because plates grind together. These may seem like violent accidents, but they're part of a deep organized flow that gravity set in motion billions of years ago. This hidden engine does more than reshape the planet. It feeds life. Volcanic activity recycles carbon, regulating the atmosphere and climate. Tectonic movement creates habitats, drives nutrient cycles, and stabilizes temperature over geological time. The world beneath us is not inert. It is alive in a gravitational sense. Even the ocean you see on the surface, owes its existence to this interior engine. Gravity holds the pressure that keeps Earth's interior active. Without that internal weight, the core would cool too quickly. The magnetic field would fade, the plates would stop moving, and the climate would drift toward extremes hostile to life. We often look up to the stars when we talk about gravity, but sometimes its most important work is happening far below our feet. Every mountain, every tectonic ridge, every drop of molten iron spinning deep inside the core is part of the same cosmic story. Falling built the planet, and falling keeps it alive from the inside out. Worlds don't last forever. Even the most vibrant planets eventually grow quiet. Their fires fade, their cores freeze, their gravity remains, but its heartbeat stops. Inside every rocky planet heat is a memory of ancient collisions, of relentless compression, of gravitational energy trapped deep within, but that memory can run out. As billions of years pass, a planet's interior slowly cools. The churning metal in the core becomes sluggish. Convection weakens. The dynamo that powers its magnetic field sputters and dies. The invisible shield collapses. Without that shield, the solar wind begins its slow, patient work. It strips away the atmosphere molecule by molecule, bleeding the sky into space. Radiation pours in unfiltered. Water evaporates and is lost. Temperatures swing between brutal extremes. The surface once alive becomes bare and silent. We can see this story written across the solar system. Mars, once a world of rivers and lakes, is now a frozen desert beneath an unprotected sky. Its core cooled, its field faded, the solar wind tore away its air, and what was once warm and wet turned cold and dead. Even Mercury tells the same tale. Its interior long frozen, its surface scorched by the sun, its magnetic whisper barely audible. It is a planet whose inner fall has already ended. When a planet's interior still moves, it can shield itself, breathe, evolve. But when gravity inside grows quiet, a world begins to age in silence. This is the slow death of a planet, not an explosion, not a dramatic end, but a cooling, a slow fading of the engine that once made everything possible. Mountains stop growing, volcanoes go extinct, the sky thins, the ground freezes, and the world forgets it ever burned. Even Earth will face this one day. Our core will cool, our shield will falter, and the sun, swollen into a red giant, will finish what time began. The falling inside will finally stop, but the gravity outside will remain. A cold planet is not a planet without gravity. It's a planet where gravity has run its course, where the energy born from its ancient fall has finally dissipated. A world that no longer shapes itself from within. Gravity built the world. Gravity kept it alive. And in the end, gravity watches as it grows silent again. Everything that falls has an end. A planet cools. A star burns out. A galaxy drifts. And one day even the universe will grow old. Right now, gravity is still winning. It builds stars from gas. It sculpts galaxies. It draws clusters toward one another in silent rivers of motion. But gravity can only work with what it has. It needs contrast places of high density and low density, a landscape down which things can fall. As time stretches forward, that landscape begins to flatten. Stars burn their fuel and fade into embers. Black holes devour what they can and then wait in silence. Galaxies drift farther apart, carried on the swelling tide of expansion. The universe grows colder, thinner, quieter. Trillions of years from now, new stars will no longer form. The last red dwarfs will gutter out. The great engines of gravity will fall silent, not because gravity has vanished, but because there is nothing left to fall. Even black holes, the ultimate monuments to collapse, will not last forever. Through Hawking radiation, they will slowly leak their mass into the void. One by one, they too will fade, leaving behind only a sea of cold particles drifting endlessly apart. This is the heat death of the universe, a time when entropy reaches its maximum, when no energy remains to be rearranged, when no gradients exist for things to fall down. It isn't an explosion, it isn't fire, it's the opposite. A stillness so vast it erases the memory of motion. In that far future, gravity will still be written into the fabric of space, but it will have nothing left to shape, no clouds to collapse, no stars to ignite, no orbits to hold. Every well will have flattened, every structure will have dissolved. The universe will not end with a bang. It will end with a long, slow exhale, a fade into perfect equilibrium, a state where falling has no meaning, because everywhere is the same. This is not a tragedy, it's a consequence of how the universe works. Every orbit, every collapse, every heartbeat of gravity moves energy from order to disorder, from difference to uniformity. This is the arrow that began with a whisper at the dawn of time and ends with silence. The cosmos began in a hot, dense, uneven state. It ends cold, thin and smooth, and somewhere between these two infinities, everything we know, every star, every planet, every thought, is just a moment in the universe's long fall towards stillness. When that day comes, there will be no more falling, not because gravity has died, but because the universe has reached its final perfect rest. For most of cosmic history, gravity ruled. It gathered dust into stars, stars into galaxies, galaxies into clusters, clusters into rivers flowing toward massive attractors. It seemed like the universe would forever be defined by falling, but then something changed. Billions of years after the Big Bang, astronomers watching distant supernovae found something strange. Galaxies weren't just drifting apart, they were accelerating away from each other. Space itself wasn't just expanding, it was speeding up. This was not gravity's doing. It was something else, something that behaves like a pressure woven into the fabric of space-time itself. They gave it a name that captures how little we understand it: dark energy. Dark energy is not a force like gravity. It doesn't pull objects together. It stretches the stage beneath them. Imagine standing on a rubber sheet that's quietly expanding beneath your feet. No matter how hard you run towards someone far away, the ground between you grows faster than you can close the distance. On small scales, gravity still wins. Planets stay in orbit. Galaxies hold themselves together. Clusters remain bound for now, but beyond those islands of stability, space is accelerating outward, carrying everything away from everything else. And the faster it stretches, the harder it becomes for gravity to connect distant parts of the cosmos. One by one, galaxies will slip beyond our cosmic horizon, not because they're moving through space, but because space itself is expanding between us. Eventually, only the closest cluster, our local group, will remain visible. The rest of the universe will fade into darkness. This is gravity's quiet defeat. Not a violent battle, a slow erosion of its reach. Falling depends on differences in density, on gradients, on the ability to pull distant things together. Dark energy flattens those differences. It stretches everything apart faster than gravity can respond. In a future dominated entirely by dark energy, the great rivers of galaxies will dry up. There will be no new attractors, no new structures. Everything will drift into the night. Even if gravity never truly disappears, its arena shrinks. Its voice grows softer. The universe will not stop falling, but it will fall into silence, trapped inside shrinking islands of matter, surrounded by an endless accelerating void. And that's the final irony. Falling gave shape to everything, but in the end the universe itself will fall into the one thing nothing can escape, the expansion of its own fabric. We began this journey with something simple, a stone falling, a planet orbiting, a galaxy drifting, a universe unfolding. What looked like stillness was never still. From the smallest atom to the largest supercluster, everything is in motion, everything is pulled, everything is falling. You're falling right now, around the sun, through the galaxy, Along the great gravitational river flowing toward distant attractors, the ground beneath you doesn't hold you still. It only pushes back against the curve of space-time that gravity has drawn. The stars above are falling too. They orbit invisible centers. They slide along the skeleton of dark matter, woven through the vast web that gravity has spent billions of years building. Even that web was born from a whisper, tiny ripples in the early universe that began the Great Cascade. Every structure that exists is a monument to falling. Planets formed because dust fell inward. Stars ignited because gravity squeezed. Galaxies gathered because the universe was unevened. Black holes emerged where the fall never stopped. Falling shaped our world from the inside too. It forged our molten core, our magnetic shield, our breathing sky. It gave us a place where life could begin, and the stability it needed to endure. But even falling has its limits. Entropy grows, energy spreads, and as dark energy stretches the universe ever faster, the reach of gravity shrinks. One by one, the great structures will drift out of sight, not because gravity failed, but because the stage beneath it changed. The universe began with a fall, and one day it will end in stillness. Yet in between those two infinities, falling gave us everything. Every star, every orbit, every heartbeat. We are the brief, bright pattern written in the middle of that descent. Everything falls, and we are part of that fall, not standing above it, not apart from it, inside it. Our lives, our history, our world are a ripple in a cosmic motion that began long before us, and will continue long after we're gone. Everything falls, and in that fall, the universe became what it is. Right now, as you stand perfectly still, you're not standing still at all. You are hurtling through space at tens of thousands of kilometers per hour, carried on a blue planet that is endlessly falling around a star, and that star isn't still either. It sweeps along a spiral arm of Milky Way, dragged into its orbit like a stone caught in a whirlpool. Even the galaxy itself is tracing a vast slow curve around something far more massive in the dark. Everywhere we look, nothing moves in straight lines. Planets orbit stars, stars orbit galactic centers, galaxies orbit each other. Even the faintest particles left adrift in interstellar space are quietly bending around something. This is one of the most elegant tricks of the universe. Give an object speed, give it gravity, and it won't fall straight, it will orbit. Orbit is balance. It's the meeting point between falling and flying, a dance where nothing ever truly lands. It just keeps missing, again and again, forever. If falling is how gravity pulls, then orbit is how the universe holds itself together. Imagine standing on a high mountain with a perfect cannon. You fire a shell. It arcs through the air and lands not far away. You fire again, but harder it goes farther. Harder still it curves around the world. And then if you give it just the right speed, something extraordinary happens. It never lands. It keeps falling, but the Earth curves away beneath it just as fast. This is orbit, not floating, not hovering, falling, but falling sideways fast enough that the ground is always out of reach. This was the insight that changed everything for Isaac Newton. He realized the same force that pulls an apple to the ground is the force that keeps the moon in the sky. The moon isn't hovering. It's falling continuously, missing Earth by thousands of kilometers every second. Orbit isn't some invisible rope pulling objects in a circle. There's no force pushing upward against gravity. The object is weightless in free fall. It's simply moving forward so fast that its path bends around the planet instead of intersecting it. This is why astronauts on the International Space Station feel weightless. They're not beyond gravity. In fact, gravity at their altitude is almost as strong as it is on the ground. They're just falling with the station, forever chasing the horizon that keeps curving away. Orbit is not a separate phenomenon from falling. It is falling, with just the right velocity to never arrive. This idea sounds simple, but it's one of the most powerful in all of physics. Because once you understand this sideways fall, you understand why planets don't crash into stars, why moons circle worlds, why galaxies trace endless curves through the dark. Orbit is falling, perfectly choreographed. For centuries, people imagined the heavens as perfect. The planets they thought moved in flawless circles, because surely the universe itself must be flawless. But the sky doesn't care about our ideas of perfection. When Johannes Kepler studied the motion of Mars, he found something strange. The data refused to fit into neat circles. The planet moved faster at some points in its path, slower at others. Its distance from the sun wasn't constant, and no matter how carefully he calculated, a perfect circle simply didn't work. So Kepler tried something else. He bent the path, and suddenly the numbers fell into place. Orbit, he discovered, isn't usually a circle, it's an ellipse. A stretched circle with the sun sitting not at the centre, but at one of its two foci. This was a quiet revolution. For the first time, the geometry of the cosmos matched the precision of the sky. Why ellipses? Because gravity isn't pulling from the centre of a circle, it's pulling from a single massive body, the sun. The shape of an orbit depends on the balance between an object's speed and the strength of that pull. Push too little and it falls in, push too much and it escapes. Push it just right and you get an ellipse. This isn't just a mathematical curiosity, it's why Earth has seasons. Our planet doesn't move in a perfect loop. It comes closer to the sun at perihelion and swings farther away at aphelion. The orbit isn't dramatic, but it's real, a slight stretch that shapes the rhythm of the year. Other worlds show this even more clearly. Mercury traces a noticeably elongated path, its speed surging as it dives toward the sun and slowing as it swings away. Comets like Halley's Comet follow ellipses so stretched they spend decades in the dark, before briefly flashing past the sun like cosmic boomerangs. The ellipse isn't the universe being imperfect, it's the universe being precise. It reflects the exact trade-off between motion and gravity. A perfect circle is just a special case, rare fragile, almost never found in nature. Kepler's ellipse opened a door. They showed that orbits are not static loops carved in space, but living paths that change speed, angle, and distance. They revealed that the dance between matter and gravity is subtle, mathematically sharp, and endlessly beautiful. And soon after Kepler, someone else would show why ellipses happen at all. An orbit isn't just a path in space, it's a delicate balance of energy. Gravity wants to pull everything inward. Motion wants to carry everything away, and somewhere in between those two impulses, a truce is made. Every object in orbit carries two kinds of energy: kinetic energy from its motion, and gravitational potential energy from its position in the gravitational well. The shape and stability of an orbit come entirely from how those two balance. If the object has too little speed, gravity wins. The orbit decays, the path tightens, and eventually it falls inward. If it has too much, motion wins. The curve opens up into a hyperbola, and the object escapes into the void. But give it just the right speed, and it falls without ever arriving. Its kinetic energy and gravitational energy weave together to form a stable ellipse. This isn't an abstract idea. It's something you can see. When a satellite launches, rockets don't just push it upward. They push it sideways. Upward gets you altitude. Sideways gives you the speed to stay there. If the engine cuts off too soon, the satellite falls back. If it's too fast, it breaks free of Earth altogether. This energy balance also explains why orbits are faster near perihelion. As an object swings closer to the central mass, it falls deeper into the gravitational well. Potential energy drops. Kinetic energy rises. The orbit speeds up. Then as it moves away again, the process reverses. The energy isn't lost, it's traded back and forth. Like a perfect cosmic pendulum, this is what keeps Earth locked around the sun. We're not hovering, We're falling inward, but our sideways speed is exactly what it needs to be to keep missing the sun at every turn, and this balance exists everywhere. Moons, planets, stars, galaxies. Each orbit is an invisible equation being solved in real time. There's no magic holding things in place, just the cold, elegant arithmetic of motion and gravity. Orbit is not about strength. It's about agreement. Not all orbits are the same. Some skim close to the surface of a planet, racing around it in just minutes. Others drift far above, circling slowly over the same world for hours or even days. What changes isn't the force of gravity alone, it's the balance of speed and distance. Near a planet, gravity is stronger. The pull downward is fierce. To keep falling without hitting the ground, an object needs to move faster sideways. Closer orbits mean higher speeds. Farther away, gravity's pull weakens. The curve of space around the planet grows gentler. The object doesn't have to rush to stay up. It can drift more slowly and still trace its endless path. This is why the International Space Station circles Earth once every 90 minutes. It flies low, roughly 400 kilometers above the surface, and must travel about 7 kilometers per second to stay there. A satellite in geostationary orbit 35,786 kilometers up moves at just 3 kilometers per second, but takes a full 24 hours to circle the planet, matching Earth's rotation so perfectly that it seems to hang motionless in the sky. These aren't arbitrary numbers. They come from the precise way gravity and velocity weave together. If you want to orbit close, you must move fast to fight the steep curve of the gravitational well. If you orbit far, you can glide slowly over the gentle outer slope. There's a kind of music to this. Every altitude has its own rhythm, a specific speed that keeps you suspended in perfect free fall. Miss a beat and the orbit changes. Too slow and you spiral inward. Too fast and you drift away forever. This relationship holds everywhere, from artificial satellites to moons and planets. Mercury, closest to the Sun, races through its orbit in just 88 days. Neptune, far out in the cold, takes 165 years. Gravity sets the tempo, distance sets the pace, and velocity keeps the dance alive. Orbit isn't about staying still. It's about moving at exactly the right speed for exactly the right distance. That perfect match is what turns falling into flight. From a distance, orbits look eternal. A satellite tracing its path, a moon circling its planet, a planet swinging around its star. Everything seems to move in perfect loops, repeating forever. But the universe is never truly still, and no orbit is perfectly stable. Even the most precise path can shift, nudged by tiny forces that build up over years, decades, centuries. Some changes are slow, some are violent. The most familiar culprit is drag. Low Earth satellites, like those on the International Space Station, fly through the thinnest wisps of the upper atmosphere. Molecule by molecule, they lose speed. Every orbit drags them a little lower, where the air thickens just enough to slow them more. Eventually, unless boosted, they spiral inward and burn in the atmosphere, a graceful end written by invisible air. Even in the vacuum of space, orbits can drift. The gravity of the moon tugs at Earth's satellites. The sun pulls unevenly. The planet itself isn't a perfect sphere. Its equatorial bulge and subtle irregularities create tiny perturbations, nudging the orbit away from its ideal path. What begins as a clean ellipse becomes a living, shifting track. Then there are tidal forces. When one object pulls strongly on another, it can transfer energy between rotation and orbit. This is why the moon is slowly drifting away from Earth. Our planet's rotation is gradually feeding its orbit, millimeter by millimeter each year. In the distant future, Earth's day will lengthen, and the moon will hang farther in the sky. Over longer timescales, the dance can get chaotic. Planets tugging on each other can destabilize orbits. Resonances can push objects into new paths. Some may be ejected entirely. Others crash inward in catastrophic spirals. Even galaxies experience this slow unraveling. Stars orbiting the center drift, interact, scatter. Their orbits are drawn out, blurred, smeared over time. The beauty of an orbit lies not in its permanence, but in its fragile balance. Every curve is a temporary solution, a moment of harmony between motion and pull. It can last for years or billions of years, but never forever. This is why satellites need periodic boosts, why planetary systems evolve, why cosmic structures are always in motion. Gravity may draw the path, but the universe keeps rewriting it. Orbit isn't carved in stone. It's a story still being written. When we imagine an orbit, we picture a small object circling a big one. The moon around Earth, Earth around the sun, a planet around a star. But in truth, that's only half the story. In the language of gravity, there is no true center. When two objects interact, they both pull on each other, and they both move. This secret lies in something called the barycenter, the common center of mass around which both objects orbit. Sometimes that barycenter lies deep inside the larger body, so it looks like only the smaller one is moving, but the larger one is moving too, just more subtly. Take Earth and the Moon. The Moon doesn't orbit the exact center of Earth. Both Earth and Moon orbit a point about 400-600 kilometers from Earth's center, a spot beneath the surface but not at the core. Earth wobbles gently as the Moon swings around. It's a cosmic dance, not a chase. In more extreme cases, the barycenter can lie in open space. That's what happens with Pluto and Charon. Charon is so massive compared to Pluto that neither truly orbits the other. They orbit a point between them, like two dancers spinning around their clasped hands. This isn't limited to planets and moons. Many stars exist in binary systems, paired together in elegant gravitational loops. Each star orbits the barycenter they share, sometimes close and fast, sometimes far apart in wide arcs lasting centuries. Even our sun moves this way. It doesn't sit perfectly still while planets circle it. The planets tug back, shifting the sun's position ever so slightly as the entire solar system orbits its own barycenter. This principle is more than a curiosity. It's a powerful tool. Astronomers use tiny stellar wobbles to detect exoplanets, worlds too distant to see directly. The planet's pull makes the star dance, and we watch the rhythm of that dance across the light years. Every orbit is a partnership. Even when one partner is small, its influence is real. Nothing is truly fixed. Everything moves. Orbit isn't one body chasing another. It's two bodies bound together around a shared invisible point. Two bodies dancing in orbit can be elegant. Their paths trace perfect ellipses around a shared center. But the universe rarely deals in twos. Add a third dancer to the floor, and the music changes. Unlike the simple two-body problem, the three-body problem cannot be solved with a neat equation. The gravitational pull of each body affects the others in a constantly shifting way. Their orbits become sensitive, unstable, and astonishingly complex. A tiny nudge at the start can create a completely different outcome later. This is what makes systems with multiple moons, multiple planets, or multiple stars so rich and so unpredictable. Picture a planet orbiting a star. Its path is smooth, regular, almost clockwork. Now add another planet. Their gravitational fields start pulling at each other, subtly warping their orbits. The speed and angle shift a little with every turn. Over time, those little tugs can add up, and the original clean ellipse can twist, stretch, or break. This is not chaos in the sense of randomness. It's deterministic chaos. Every motion follows precise laws, but the system is so sensitive to its starting point that prediction becomes nearly impossible after enough time. The solar system itself lives inside this delicate balance. The planets tug at one another constantly. Over millions of years, their orbits can drift, tilt, or even eject a member entirely. What seems steady to us now is really a slow, ongoing gravitational argument. This is why computer models are crucial in modern astrophysics. We can't solve the n-body problem analytically, but we can simulate it step by step, watching how the future unfolds second by second. It's also why systems like TRAPPIST-1, with many planets packed tightly together, are so fascinating to study. Their orbits can be stable, but only just barely, and sometimes chaos builds to a breaking point. A planet gets nudged into a new path, a moon is flung outward, a star escapes its system forever. Cosmic order gives way to cosmic improvisation. Orbit is not always smooth. When gravity becomes a crowd, even perfect laws can produce wild, unpredictable dances. In a universe where orbits can spiral, drift, or break apart, it's almost miraculous that some systems remain stable for billions of years. The solar system has been moving in rhythm since before life began. Planets follow their paths like clock hands, not perfectly, but reliably enough for worlds to endure. Why? Because gravity, though it can create chaos, can also build harmony. One of the most powerful stabilizing forces in orbital mechanics is resonance. When two or more bodies move in orbits that line up in repeating ratios, their gravitational tugs reinforce each other in predictable ways. Instead of knocking the system out of balance, they lock it into a repeating pattern. Take Jupiter and Saturn. Their orbital periods are close to a 5. 2 resonance. Every time Jupiter completes 5 orbits, Saturn completes roughly 2. This resonance keeps their paths from colliding and dampens the chaotic drift that might otherwise tear the outer solar system apart. Or look at Pluto and Neptune. Even though Pluto's path crosses Neptune's, the two never collide. They're caught in a 3. 2 resonance. Their orbits weaving around each other like gears in a cosmic clockwork. Resonance isn't the only stabilizing effect. Tidal interactions can synchronize orbits and rotations, leading to states like tidal locking, where one side of a moon forever faces its planet, as with the Moon and Earth. This synchronization removes energy from the system, calming its motion over time. The distribution of mass also matters. Large planets like Jupiter act as gravitational anchors, absorbing or deflecting stray objects that might destabilize the inner system. They're like heavy dancers at the center of the floor, keeping everyone else roughly in step. Even in multi-body chaos, some arrangements are self-correcting. If an orbit shifts slightly, gravitational forces can nudge it back toward equilibrium. These subtle feedback loops can keep systems stable for unimaginable stretches of time, but stable doesn't mean static. The solar system isn't frozen, it breathes. Orbits slowly change tilt and precess, but the structure holds, a living balance, not a fragile one. This stability is why Earth can host life. Our orbit is steady enough to keep the climate within survivable bounds. For billions of years, without that quiet gravitational harmony, complex life would never have had the time it needed to arise. Orbit is not just motion, it's choreography. Sometimes wild, sometimes delicate, but when it works, it can last longer than any star. Orbit is not alone. Every world spins, every star rotates, every satellite carries its own internal motion. And when those spins meet the pull of gravity, something remarkable happens. Spin and orbit are two faces of the same dance. Orbit is the path through space. Spin is the rotation on the spot. But in a gravitational system, these two motions don't stay separate for long. They talk to each other through tidal forces. When one body spins while orbiting another, its near side feels a stronger gravitational pull than its far side. That difference stretches it ever so slightly, raising tides not just in water but in rock. Those tides don't line up perfectly with the direction of pull. They lag behind, and that tiny lag transfers energy between spin and orbit. Over time, this exchange can change both. It's why the moon always shows the same face to Earth. Long ago it spun freely, but tidal forces drained its rotational energy, locking its spin to its orbit, a state called tidal locking. Now it turns once per orbit, forever frozen in that quiet alignment. It also works the other way around. Earth's own spin is slowly feeding the moon's orbit, pushing it outward by a few centimeters each year. Our day lengthens, the moon drifts away, and the system keeps evolving. Tidal locking is common across the cosmos. Many moons in the solar system are locked to their planets. Many exoplanets are locked to their stars, showing one face in endless day, the other in endless night. Spin affects more than just locking. Rapid rotation can bulge a planet at the equator, shifting its gravitational field and subtly altering the orbit of its satellites. Spin axes can wobble precession, introducing long, slow cycles in orbital behavior. Even the tilt of a world can change its climate and orbital stability over geological time. This spin-orbit coupling is everywhere. It's written into the shape of planets, the rhythm of moons, and the evolution of entire star systems. In the end, orbit is not a perfect geometric curve. It's a living path moulded by the spins of the bodies involved. And those spins in turn are slowly sculpted by the orbit itself. They are not partners who occasionally meet. They are bound, forever influencing each other, in a slow, silent conversation across the void. Most orbits in the universe follow the familiar logic of Newton. Objects move, gravity bends their paths, and they trace elegant ellipses through the dark. But near a black hole, that familiar logic collapses. Here gravity isn't just a pull, it's the curvature of spacetime itself. Every path bends inward more sharply than intuition allows, and orbiting becomes something stranger, faster, more fragile. A black hole doesn't have a solid surface. It has an event horizon, a boundary beyond which no path leads out again. As you approach it, orbits become unstable. Get too close, and no amount of speed can save you. But there's a critical threshold, the innermost stable circular orbit, or ISCO, for a non-spinning black hole that's 3 times the Schwarzschild radius. Inside that distant stable orbit is impossible. Any object crossing that line spirals inward, dragged unstoppably into the dark. Above ISCO orbits are still possible but different. They're not gentle ellipses. They're warped, time-stretched, curving through a geometry that twists both space and time. An observer far away would see objects move slower and slower. As they approach the horizon, their light stretched and dimmed by gravitational redshift. If the black hole spins, and most do, the situation grows even stranger. Its rotation drags space-time itself around with it, a phenomenon called frame dragging. This creates a region called the ergosphere, where no object can remain still. Everything is forced to move in the direction of the spin. Frame dragging twists orbits like ribbons in a whirlpool. It allows matter to orbit closer than ISCO for non-spinning holes, and even extract energy from the black hole itself. This is what powers some of the brightest engines in the universe. Accretion disks spinning at near-light speeds, launching jets across galaxies. Even light can orbit here. At a specific distance lies the photon sphere, a thin, unstable track where light circles the hole again and again, before escaping or plunging in. No orbit lasts forever there. A single nudge sends it flying or falling. These extreme orbits are not science fiction. They shape real astrophysical objects. The flickering of X-rays from accretion disks, the warped light seen by Event Horizon Telescope, the way stars dance near the centre of Milky Way, revealing the supermassive black hole Sagittarius A. Orbit near a black hole is not just motion. It's a glimpse of how the universe behaves when gravity is no longer gentle, but absolute. So far, we've followed orbit from the small to the extreme, from satellites skimming above a planet, to planets circling stars, to stars tracing warped paths around black holes. But orbit doesn't end there. It climbs higher to entire galaxies. Our star, the Sun, is not fixed in space. It's moving at more than 220 kilometers per second, tracing a vast orbit around the centre of Milky Way. This journey takes about 230 million years to complete. One full galactic year In the time since the dinosaurs walked the Earth, our solar system has completed just a single lap. This orbit isn't around a solid object. The galactic center is a dense concentration of mass, billions of stars, clouds of gas dark matter, and a supermassive black hole. Sagittarius, together they generate the gravitational well that bends the paths of every star. The Milky Way itself is spinning. Its spiral arms are not rigid structures but patterns, like waves in a sea of stars. Each star orbits at its own speed, carving a path that's part of a larger gravitational flow. And the galaxy is not alone. Around it swarm dozens of satellite galaxies, small companions like the Large Magellanic Cloud and Small Magellanic Cloud. They orbit the Milky Way the way moons orbit planets, pulled along invisible curves that span hundreds of thousands of light years. Some are slowly being torn apart, their stars stretched into tidal streams that wrap around the Milky Way like ribbons of starlight. Even giant galaxies orbit something. The Milky Way and Andromeda Galaxy are locked in a slow gravitational embrace, drawing closer at 110 kilometers per second. In about 4 billion years, their paths will merge into a titanic collision, a ballet of stars and dark matter unfolding over eons. They are both members of the local group, which itself orbits the deeper gravitational well of the Laniakea Supercluster. These motions are so slow we can't see them in a human lifetime, but over cosmic timescales, they draw enormous arcs across intergalactic space. Galaxies fall toward each other, cluster into groups, and orbit massive dark matter halos, like stars orbiting galactic cores. Orbit at this scale becomes a gravitational hierarchy. Stars orbit galaxies, galaxies orbit clusters, clusters orbit superclusters, each level nested inside the next. We live inside that motion, right now as Earth spins and orbits the Sun, as the Sun orbits the Milky Way. The Milky Way itself is tracing its own arc through the deep, dark ocean of the universe. The curve never ends. It only grows larger. From orbiting satellites to orbiting galaxies, every step so far has revealed motion tied to something larger. But what happens when you zoom out farther than superclusters? When the entire sky becomes a map of billions of galaxies, a new pattern appears, one that stretches across the cosmos like threads in a vast invisible web. The cosmic web is not a poetic idea. It's the real architecture of the universe, a colossal network of filaments made mostly of dark matter, with galaxies and clusters strung along them like dewdrops on threads. In between lie enormous voids, vast dark regions almost empty of matter. In this structure, galaxies don't drift randomly. They flow. They slide down the gravitational slopes carved out by invisible dark matter. They orbit along filaments, are pulled into clusters at the intersections, and slowly spiral toward massive attractors over billions of years. Our own Milky Way is part of one of these streams, moving toward the Great Attractor, a region so massive it bends the motion of entire galaxy groups. Every second we travel hundreds of kilometers through this cosmic current, not because space is pushing us, but because gravity is pulling us along an invisible path. This is orbit on the largest scale known. The Milky Way and its neighbours don't have a simple circular trajectory. They move in complex curves, woven into the geometry of the cosmic web itself. Some filaments are stable, others collapse slowly into larger structures. Over time, these flows feed galaxy clusters, like rivers feeding an ocean. Dark matter provides the skeleton for this dance. Though we can't see it, its gravity is the stage on which every galaxy moves. The luminous matter we observe is only the glowing surface of a much deeper structure. These cosmic flows aren't fast on human timescales. They take hundreds of millions of years to reveal their shape, but they define the ultimate fate of galaxies, where they gather, where they merge, where their journeys end. Orbit began with stones and satellites. It extended to planets, stars, and galaxies. But here at the scale of the universe itself, it becomes something grander, a gravitational river winding through the cosmic web, carrying entire galaxies like leaves on an unseen current. Life doesn't just need light, it needs consistency. A planet bathed in sunlight one day and frozen the next would never give life time to take hold. And the quiet architect behind that consistency is orbit. Earth's orbit around the Sun is a gentle ellipse, not a perfect circle, but close enough. This near-constant distance keeps the flow of energy from the Sun steady, allowing oceans to stay liquid, air to stay breathable, and climates to remain within a narrow livable range. This delicate balance isn't a cosmic accident. It's a physical consequence of gravitational dynamics. The combination of our orbital shape, our distance from the Sun, and the tilt of Earth's axis creates the rhythm of the seasons, regular cycles that have shaped the evolution of every living thing on this planet. If our orbit were more eccentric, the swings between summer and winter would be devastating. Half the year might bring boiling heat, the other half deep freeze. If our orbit were unstable, the climate would drift chaotically over time. Stability is what allows complex life to build, persist, and adapt. Orbit doesn't just set temperature, it sets time itself. Years are defined by one lap around the Sun, seasons by the angle and path of that lap. Even life cycles, migration, reproduction, hibernation, are synced to the orbital rhythm of our world. And Earth is not unique in this. In the hunt for exoplanets, astronomers search for worlds in the so-called habitable zone, not just at the right distance from their stars, but in stable orbits that can hold that distance over eons. A planet can have the perfect ingredients for life, but if its orbit wobbles wildly, its oceans may boil away or freeze solid before life has a chance to begin. The quiet stability of Earth's orbit owes much to other players in the solar system. The Moon helps steady our axial tilt. Jupiter acts as a gravitational shield, sweeping up potential threats and adding stability to the orbital structure. And the resonance among planets keeps the system in balance. Orbit is more than geometry. It's an invisible scaffold on which life is built. Every tree, every breath, every heartbeat echoes the path our planet takes through space. Without stable orbit, there is no stability at all. Orbit doesn't just hold a planet steady, it makes it breathe, not in seconds or years, but in slow, deep rhythms that play out over tens of thousands of years. These are the hidden beats of Earth's climate, and they are written in our orbit. Earth's path around the Sun is not fixed, it shifts and wobbles with time. In three main ways: eccentricity, axial tilt, and precession. Together, these form what scientists call Milankovitch cycles. Eccentricity is the shape of Earth's orbit, sometimes nearly circular, sometimes slightly stretched into an ellipse. This cycle takes about 100,000 years. When the orbit is more eccentric, seasonal differences grow stronger. When it's rounder, they soften. Axial tilt is the angle of Earth's spin relative to its orbital plane. Today it's about 23.5 degrees, but over 41,000 years it slowly rocks back and forth between 22 and 24.5 degrees. A greater tilt means more extreme seasons, colder winters and hotter summers at high latitudes. A smaller tilt brings milder climates. Precession is a slow wobble in the direction Earth's axis points, like a spinning top that isn't perfectly upright. Our planet's axis traces a slow circle every 26,000 years. This changes when each hemisphere leans toward the Sun, altering the distribution of sunlight between seasons. Individually, these effects are subtle, but together they shape the grand climate cycles of our planet. They determine when glaciers grow, when they retreat, when deserts expand, and when green returns. The record is carved in stone and ice. Ancient sediments and polar ice cores show a heartbeat, warm periods rising and falling in step with orbital variations. Every ice age, every interglacial bloom has been triggered and timed by these silent shifts in Earth's path. These cycles don't act alone. They interact with the planet itself, with ocean currents, atmospheric chemistry, and reflective ice cover. A small nudge from orbit can tip Earth into a deep freeze or lift it into a warm, fertile interglacial. And though these changes happen slowly, their imprint is profound. They've shaped the landscapes we live on, the ecosystems that thrive, even the course of human evolution. Orbit doesn't just give Earth stability, it sets the rhythm of its long, slow breath. A cosmic metronome ticking beneath everything we know. Orbit feels eternal. Every year Earth returns to the same place, following the same curve around the Sun, but nothing in the universe is truly permanent. Even orbits drift. On short timescales, those shifts are tiny, barely noticeable across centuries. But stretch the clock to hundreds of millions or billions of years, and the path of Earth begins to change. One of the main forces driving this drift is the slow evolution of the Sun itself. Stars are not static furnaces. They change, growing hotter and brighter with age. In about 1 billion years, the Sun's luminosity will be roughly 10% higher than today. That may not sound like much, but it's enough to push Earth's delicate energy balance over the edge. As the Sun grows stronger, the region of the habitable zone, the comfortable shell where liquid water can exist, will shift outward. Earth, once perfectly placed, will find itself in a hotter, less stable orbit, bathed in too much sunlight. Long before the Sun becomes a red giant, our oceans may boil away, the atmosphere may be stripped, Earth's orbit itself will remain, but the conditions that orbit sustains will vanish. Meanwhile, other forces act more slowly but just as relentlessly. The gravitational tugs between planets accumulate over time. These tiny nudges can, over hundreds of millions of years, alter eccentricities, inclinations, and orbital resonances. Computer models of the solar system show a small but real chance that inner planets could enter chaotic motion in the distant future, their paths warping unpredictably, collisions or ejections not entirely ruled out. And then there's the Sun's own fate. In about 5 billion years, it will swell into a red giant, engulfing the inner system in a storm of stellar wind. Its mass will decrease as it sheds its outer layers. Less mass means weaker gravity. The orbits of surviving planets will expand outward, their paths growing wider and slower. Earth's orbit will drift too, but by then our world may no longer exist as we know it. Eventually the Sun will collapse into a white dwarf, a dim ember of its former self. What remains of the solar system will settle into new fragile orbits, a quiet echo of the dance that once was. Orbit is not immune to time. It evolves with the stars it serves, nudged by neighbours, reshaped by stellar death. Even the most stable path is just a chapter in a much longer story. The curve that holds us today will not hold us forever. Orbit is balance. It's the gentle tension between motion and pull. But even balance has an expiration date. As the universe grows older, the great orbits that define its structure will begin to unravel. Right now, gravity is the main sculptor of motion. It holds galaxies in clusters, clusters in superclusters, and draws everything along the invisible filaments of the cosmic web. But gravity has an opponent, dark energy, the mysterious pressure woven into spacetime itself. Its quiet push is making the universe expand faster and faster. For billions of years, gravity and expansion have existed in a fragile truce. Galaxies orbit one another in clusters. Superclusters drift together through space. But as the expansion accelerates, dark energy will slowly pull these structures apart. Far in the future, galaxies outside our local group will slip beyond the cosmic horizon. The space between us and them will stretch faster than light can cross. Their orbits will cease to be meaningful. They'll be carried away by the expansion of space itself. Clusters that once orbited each other will dissolve into isolated islands. The cosmic web will thin out, its filaments snapping under the pressure of endless expansion. No matter how strong gravity is locally, beyond a certain scale it can't fight the tide. Inside these shrinking islands, orbits will continue for a time, stars around galactic centers, planets around fading stars. But even those paths are finite. Stars will burn out, galaxies will dim, black holes will dominate the centers, and even their orbits will slowly decay through Hawking radiation and gravitational interactions. As energy spreads thinner and thinner, the differences that allow orbit to exist, density gradients, massive attractors, will flatten away. With no structures to orbit, motion becomes meaningless. The great cosmic dance will come to an end, not with a collision, but with a silence. In this far future, the last orbits will be around black holes, and then when even those fade, nothing will remain to circle anything, only particles drifting apart. In a dark frozen cosmos, orbit built the universe, and one day, orbit will end with it. Everything orbits something. A stone thrown from a hand, a satellite circling a world falling forever around its star, a star tracing a silent curve through the galaxy, a galaxy sliding along invisible threads in the cosmic web. Orbit is not a rare event. It is the architecture of motion. It's how gravity and velocity make peace, how the universe builds structure without collapse, how chaos finds its temporary harmony. For as long as gravity has shaped space, orbit has been its signature. It has given planets their stable skies, stars their spiral homes, galaxies their cosmic rivers. It has given Earth its seasons, its rhythm, its life. Every orbit is a story of balance, a planet balancing the pull of a star balancing the pull of a galactic core, a galaxy balancing the invisible weight of dark matter, a cosmos balanced on the edge between gravity and expansion. But orbits are not eternal. They wobble, they drift, they dissolve. They are as mortal as the structures they bind. One day, even the grandest orbits, those of galaxies, clusters, and cosmic flows, will unravel into silence. And yet, the impermanence doesn't make them meaningless. It makes them extraordinary. For billions of years, orbit has been the framework on which stars were born, worlds were built, and living things emerged to look up and wonder. Right now, as you stand beneath the sky, you are orbiting too, around the sun, around the galactic core. Through the cosmic web, you are part of that endless curve, not watching it from the outside, inside it. Always moving, always falling, always orbiting. Orbit is the quiet order hidden in the vastness, the skeleton beneath the chaos, the line that gravity draws in the dark. And for a brief, brilliant moment, we get to ride along that line and call it home. It begins not with silence, but with motion. Even when everything around us seems still, the ground beneath our feet is moving through a vast ocean of stars. We are passengers on a colossal structure, a spiral made of hundreds of billions of suns, threaded with invisible matter, spinning through the dark. Milky Way is not just our home galaxy, it is a living system, ancient, dynamic, and constantly changing. Every star, every cloud, every particle is part of a delicate gravitational ballet. And what we know about it is astonishing. Our galaxy stretches across more than 100,000 light-years, its disk so wide that light itself would take a human lifetime just to cross a fraction of it. It's a barred spiral, a shape sculpted by gravity over billions of years, with a dense central bar and majestic spiral arms that twist outward like cosmic rivers. But it's not a solid object. Milky Way is a flow. Stars orbit at different speeds. Gas drifts through arms. Dark matter binds it all together in a halo so vast we can't see its edges. The entire structure spins at hundreds of kilometers per second. Yet we don't feel a thing. To us it's invisible motion. The galaxy is old, older than Earth, older than the sun. It formed from ancient fragments more than 13 billion years ago, long before our world existed. In that time, it's grown by devouring smaller galaxies, reshaping itself again and again, and it's still growing. We're not sitting in the center of it all. We're out on one of its spiral arms, orbiting the galactic core like a leaf caught in a slow, silent current. One full orbit takes about 230 million years, a single galactic year. The last time our solar system was in this position, dinosaurs had just begun to rule the Earth. Every star you've ever seen belongs to this galaxy. Every night sky is just a keyhole view of something so immense it defies intuition. And beyond what we can see, there are layers of structure, invisible fields, hidden mass ancient scars of collision that shape the galaxy's destiny. 100 truths are waiting here, some bright and simple, others buried in the dark. To understand them, we have to journey through the Milky Way itself, not from the outside, but from where we already are, inside it. The Milky Way is not a cloud, not a disk, and not a flat plate drifting in space. It's a layered, twisted structure, a spiral with depth scars and hidden skeletons. At its heart lies a dense central bulge, a crowded sphere of ancient stars wrapped around a massive black hole. From this core, a bar of stars stretches outward like a cosmic spine, tens of thousands of light years long, rotating slowly, pulling entire spiral arms in its wake. This bar is one of the defining traits of our galaxy. We live not in an ordinary spiral galaxy, but in a barred spiral, a more complex and dynamic shape. Beyond the bar, the spiral arms unfurl like rivers of light. Each arm isn't made of solid matter, but of stars, dust and gas flowing through gravitational waves. Patterns of density, where matter bunches together as it moves. Stars are born in these arms, drift away, and new stars take their place. The arms are not fixed, they are living, shifting patterns. The disk of the Milky Way is thin but vast, around 100,000 light-years across, and only about 1,000 light-years thick. This is where most of the stars are, including our Sun, orbiting in a giant flattened whirlpool of matter. But the disk isn't perfectly flat. It bends and warps at the edges, a gentle twist shaped by past collisions with smaller galaxies. This warp makes the galaxy look like a soft wave frozen in space. We don't live in a clean geometric diagram. We live inside a distorted spiral, a cosmic sculpture built over billions of years. Above and below this disk floats a halo, a ghostly sphere of old stars and invisible dark matter. This halo doesn't shine like the disk, but it dominates the galaxy's mass, holding everything together in its gravitational grip. And out on one of the spiral arms, halfway between the galactic center and the cold edges of the disk, is a small yellow star, our Sun, our home. What looks like a single glowing streak across the night is actually a vast layered system. A central bar, spinning arms, swirling disk-warping halo wrapping it all like a cocoon. We aren't orbiting a single star. We are moving inside an entire architecture of motion, a structure so enormous that even light would need 100 millennia to cross it. This is the shape of our home, and it's far stranger than the pictures we draw in textbooks. At the center of our galaxy, there isn't a lighthouse. There's a shadow that rules by gravity. Between curtains of dust and gas, radio and infrared telescopes reveal a crowded stage. Young hot stars whipping around an invisible point, old stars moving like sparks in a furnace. Filaments of gas curling and snapping as if tugged by an unseen hand. Nothing here drifts. Everything is held. Their hidden anchor is Sagittarius A, a supermassive black hole. Not a hole in the way a pit is a hole, but a place where space and time bend so deeply that every path curves inward. We don't see the black hole itself. We see its signature, stars tracing tight loops, light stretched and reddened near the edge. Occasional flares when a pocket of gas wanders too close and is ripped heated, made to glow before it vanishes. The neighbourhood around Escarret is extreme. Stellar orbits are measured not in calm circular sweeps, but in sharp ellipses that swing close then fling outward again. Each loop is a test of gravity in its purest form. Some stars complete these daring arcs in just a handful of years. A blink for the galaxy, long enough for us to watch them change their speed and direction in real time. From those motions, we read the mass of the invisible object at the centre, a few million times the Sun compressed into a region smaller than the orbits we track. Closer in space becomes treacherous. Gas clouds stretch into streamers. Magnetic fields twist like braided wire. Friction and shock waves turn cold gas into radiant plasma, feeding a thin, hot accretion flow that sometimes brightens suddenly. Brief heartbeats from the dark. The central bulge around all this is a city of stars, ancient populations mixed with bursts of youthful clusters, chemistry richer than the outer disk, motions crisscrossing like traffic at rush hour. The bar of the galaxy funnels material inward, whispering momentum away until gas has no choice but to sink. Here gravity recycles matter. Clouds collapse into stars. Stars die and seed the region with heavier elements. New clouds form again. Creation and consumption share the same address. Dust hides much of this from ordinary eyes. That's why we learn to listen in longer wavelengths. Infrared light that slips through the haze, radio waves that map spirals of ionized gas, X-rays that flare when something is torn and heated near the brink. Piece by piece, these windows sketch a living diagram of the core. The black hole's spin likely drags spacetime itself, tilting the orbits of gas and stars, nudging the inner flow into warped precessing patterns. Time runs differently here, not as a metaphor but as a measurable effect of strong gravity. A clock carried on a tight orbit would tick more slowly than one far away. In the core, this isn't philosophy, it's scheduling, yet the centre is not only violent, it stabilizes. By anchoring the galaxy's deep potential well, the core helps set the pace at which the bar turns, and the spiral pattern breathes. Too quiet a heart and the inner disk would drift. Too active and the bar could choke on its own inflow. Balance is the miracle. Enough gravity to hold the plan. Enough turbulence to keep the material cycling. So when you hear supermassive black hole, don't picture an isolated monster. Picture an engine room. Pipes of gas in and out. Valves that open as orbits precess. Pressure that rises and falls in luminous pulses. An invisible flywheel that keeps the galaxy's choreography in time. The Milky Way's centre is not our destination, but it is our reference point, the place that defines a round for everything else. From here outward, every arm, every cloud, every star dances to a rhythm set by a darkness. We can weigh map and even watch flicker, but never truly see. From the core outward, the galaxy unfurls, not in straight lines, but in grand curling arms that sweep through space like frozen waves. They are the most recognizable feature of our galaxy, and also one of its most misunderstood. The spiral arms are not solid structures. They are patterns, density waves moving through the galactic disk. Imagine traffic on a highway. Cars flow, but the traffic jam itself holds its shape and drifts slowly forward. That is how these arms work. Stars, gas and dust flow through them, but the arms themselves are the jam, the places where matter bunches up for a while. There are several primary arms in the Milky Way. 2 of them dominate the outer disk, and 2 smaller arms weave closer to the centre. Our own star, the Sun, is not sitting on a major arm. Instead, it lives in a small spur between them, a bright lane called the Orion Arm. This is like standing on a side street between 2 galactic highways. The spiral arms rotate more slowly than the stars themselves. Each star races ahead and then eventually drifts back into the arm again, a rhythm that repeats over hundreds of millions of years. This difference between stellar speed and pattern speed is what keeps the arms from winding up and disappearing. They are stable, flexible and persistent. Inside these arms, new stars are born, As gas clouds enter a denser region, they are compressed. Gravity takes over and they collapse into brilliant young clusters. This is why spiral arms glow so brightly. They're full of hot, short-lived stars blazing with blue light. When these stars die, the next generation is already forming nearby. The arms are both cradle and graveyard. But these elegant shapes are not smooth. They are threaded with dust lanes, dark rivers of gas and interstellar grains that cut across the light. These dusty regions block visible light but glow in infrared, revealing cold nurseries hidden behind their veils. The same dust that hides the heart of the galaxy also weaves through its arms like smoke in water, and the arms themselves are not perfectly flat. The outer disk of the Milky Way warps upward and downward like a slow, gentle wave. This warp is a scar, evidence of gravitational encounters with smaller galaxies that once brushed past and twisted the edges. From above, the Milky Way would look like a glowing pinwheel, with a bright bar in the centre and spiral arms stretching out in soft arcs. From within, it's harder to grasp. We can only map it through the positions of stars, the movement of gas, and the faint signatures of hydrogen. These arms are the living rhythm of the galaxy. They shape the flow of gas, the birth of stars, and the journey of our own solar system through space. We're not stationary passengers. We are riding the spiral. The Milky Way is not built from stone or steel. It is built from stars, each one a sphere of plasma, forged by gravity and burning for millions or billions of years. Together they shape the galaxy's light, its weight, and its history. Astronomers estimate there are hangtram tingoi sao in our galaxy, perhaps niuhon motngin lanson goitungsong trentreikat. Most are small, faint red dwarfs, barely visible even with powerful telescopes. A smaller fraction are stars like our Sun, bright enough to dominate their surroundings, and a tiny rare few are massive giants, shining with the brilliance of thousands of suns. Living fast and dying young, these stars are not evenly scattered. They form patterns, layers and families. Most belong to the galactic disk, where they orbit in vast, nearly circular paths. Here younger stars are common, formed recently in the spiral arms. They burn hot and bright, often surrounded by gas and dust. Farther out and far above the plane of the disk lie the ancient populations. The stellar halo is home to some of the oldest stars in the galaxy, stars that formed more than a mioibatinum truo. Long before the sun was born, they are poor in heavy elements, their light softer, colder, their orbits tilted in every direction like scattered seeds. Between these extremes are the star clusters, stellar families bound by gravity. Open clusters are loose gatherings of young stars, like fireflies caught in the same breeze. They drift apart over time. Globular clusters are different. They are dense, ancient and resilient, spheres of hundreds of thousands of stars orbiting the galactic halo. They are fossils, living witnesses of the galaxy's earliest days. Some stars move at ordinary speeds, others do not. A few rare outcasts are hypervelocity stars, flung out of the galactic center or torn free by gravitational encounters. They cross the galaxy at incredible speeds, on paths that may never return. And while each star is a single point of light to the naked eye, many are not alone. Binary and multiple star systems are common, with two or more suns orbiting a shared center of mass. Some whirl tightly together, others drift far apart, locked by gravity in an elegant, silent dance. Every star contributes to the Milky Way's gravitational fabric. They move, collide, evolve and die. Supernovae enrich the gas between them with new elements, feeding the next generation of stars. In this way, the galaxy is not static. It is self-renewing, and somewhere out on a minor spiral spur, around an ordinary yellow star, on a tiny rocky world, a species looks up and wonders how many suns there truly are. The Milky Way does not end where the stars fade. Beyond the glowing disk, past the spiral arms and clusters, lies a vast invisible structure. It has no light, no colour, no edges we can see, but it outweighs everything that shines. This is the dark matter halo. Dark matter is not made of stars, gas or dust. It does not emit, reflect or block light, but it has gravity, and gravity is enough. It holds the galaxy together, binding stars that should have flown away long ago. Without it, the Milky Way's spinning disk would unravel like a carousel with no axle. Astronomers first uncovered this invisible mass by studying the speed of stars. Near the galactic center, stars move quickly. Farther out, they should slow down. Just as planets orbit more slowly the farther they are from their star, but the stars at the edge of the galaxy do not slow down. They race through space too fast for the visible mass to explain. Something unseen is anchoring them in place. That something is a halo of dark matter. Its mass is estimated to be around 10 times greater than all the stars, gas and dust combined. Its size stretches well beyond the visible disk. Perhaps more than 300,000 light-years from the galactic center, the halo envelops the Milky Way like a transparent cocoon. We cannot photograph it, but we can trace its pull. The rotation curve of the galaxy, a plot of stellar speeds versus distance, remains almost flat. Instead of dropping away, that flat line is dark matter's signature. An invisible hand gripping the stars, globular clusters orbit through this darkness, swinging in long, elegant arcs around the galactic center. Streams of ancient stars curve and bend, their paths shaped not by what we see, but by what we don't. Dark matter is the skeleton of the galaxy. It sets the scale of the Milky Way, defines the strength of its gravity, and stabilizes its spinning disk. It even shapes the orbits of the satellite galaxies. Tiny companions like the large Magellanic Cloud, guiding them along unseen rails. We still don't know what dark matter truly is. It might be made of exotic particles, or something even stranger, but its effects are undeniable. Every star, every orbit, every motion we see happens inside this invisible halo. The stars are the face of the Milky Way. Dark matter is its bones. The Milky Way was not born in peace. It was built in battle, shaped by collisions, mergers, and a slow gathering of cosmic debris. Its smooth spiral structure hides a violent past. More than 13 billion years ago, the first building blocks of our galaxy were small, chaotic dwarf galaxies. They were bright, unstable, and crowded with young stars. Gravity pulled them together over cosmic time. They collided, merged, and became something larger. A growing gravitational seed that would evolve into the Milky Way. The outer halo of the galaxy still carries the fingerprints of these ancient encounters. Across the sky, tidal streams stretch like ghostly ribbons, rivers of stars torn from galaxies that no longer exist. They are not random lines of light. They are fossils, recording the collisions that built the galaxy's skeleton. One of the most important events in this story is known as the Gaia Sausage Enceladus merger. Billions of years ago, a dwarf galaxy plunged into the Milky Way. Its stars and clusters were absorbed, leaving behind tilted, stretched orbits that still sweep through the halo today. This single merger reshaped the early disk, thickened it, and changed the structure of the galaxy forever. The Milky Way continues to grow in the same way. Right now it is absorbing the Sagittarius dwarf galaxy, a small fragile neighbour being slowly torn apart. Its stars stream across the sky like light from a shattered necklace, wrapping around the Milky Way as they fall inward. Each merger leaves behind more than stars. It leaves behind energy, angular momentum and structure. The central bar may owe some of its strength to ancient impacts. The warp in the outer disk may be a ripple frozen in place from long-vanished galaxies. We can still read this history by measuring how stars move. Modern surveys like the Gaia mission track the positions and velocities of billions of stars. From this data, astronomers can rewind the clock, reconstructing the hidden choreography that shaped our home. The Milky Way is not a quiet island. It is a survivor of countless collisions. each one leaving behind traces in its halo, its disk, its very shape. And the story is not over. Another collision far greater than any before is already on the horizon. Our star is not fixed in space. It is on a long orbit, drifting through the galaxy like a tiny boat carried by a vast cosmic current. Every second the sun moves, and with it every planet, moon, and living thing on Earth. The sun is located about 27,000 light-years from the galactic center. It sits on a quiet stretch of the Orion Arm, a small spur between two of the Milky Way's major spiral arms. This position is more than just a location. It is a perfect balance. We are far enough from the violent galactic core to avoid its chaos, but close enough to remain part of the galaxy's vibrant star-forming disk. Our star completes a full orbit around the galactic center in about 230 million years. That is one galactic year. The last time the sun was in this position, dinosaurs were just beginning to dominate Earth. Human civilization in comparison is a flicker, a fraction of that orbit. The sun's orbital speed is astonishing. It travels at roughly 220 kilometers per second, fast enough to circle the galaxy while barely leaving a ripple in the stars around it. And yet we feel none of this speed. To us the sun seems still, but the sun's path is not a perfect circle. It gently oscillates up and down through the galactic plane, like a leaf riding the surface of a slow wave. Each rise and fall takes tens of millions of years. This vertical motion is part of the rhythm of the disk, a quiet heartbeat we cannot feel but can measure. Over cosmic time, the solar system does not stay in one galactic neighborhood. It slowly drifts through different regions, sometimes through quieter interarm zones, sometimes crossing spiral arms rich in gas and newborn stars. Some scientists suggest that these changing surroundings may influence conditions on Earth, subtly shaping its climate and environment over millions of years. The sun's journey is layered. It orbits the galactic center. That center orbits within the local group, and the local group itself is carried through the cosmic web. We are riding on multiple orbits at once, drifting through the universe inside a vast invisible flow. Everything we've ever known, every mountain, every breath, every heartbeat, has happened on a moving world, around a moving star, inside a moving galaxy. The sun's journey is not a story we watch, it is a story we live. We often picture galaxies as silent frozen spirals drifting through space. But the Milky Way is anything but frozen. It moves, it breathes, it changes. Right now, as you hear these words, our galaxy is in motion. At its center, the bar of stars slowly rotates like the axle of a cosmic wheel. This rotation is not fast, but it exerts a quiet power. It shapes the entire spiral pattern, guiding the flow of gas inward toward the core, setting the rhythm for the arms to follow. The spiral arms themselves are restless. They are not rigid structures, but waves, rippling, bending, and twisting over time. Gravitational tugs from satellite galaxies, the pull of dark matter, and the internal flow of gas all contribute to this dance. The shape of the Milky Way is constantly being rewritten. Star formation continues across the galaxy. Massive molecular clouds collapse, birthing new stars inside the spiral arms. In the galactic center, gas swirls inward toward the black hole, occasionally flaring with bursts of energy. Every few years, a star is born somewhere in the Milky Way, and another quietly fades away. The disk itself ripples like the surface of a slow ocean. This galactic warp is thought to be a remnant of past interactions, a scar written into the structure. It shifts gently over time, reminding us that the galaxy remembers its collisions. The halo is alive too. Ancient tidal streams drift through it, remnants of smaller galaxies long since devoured. Tiny satellites orbit in looping paths, their slow descent stirring the outer regions like pebbles dropped into water. Vast flows of hydrogen gas surround the galaxy, drifting inward over millions of years. This infall feeds the next generations of stars. a steady breath that keeps the Milky Way alive. Even the rotation of the disk is uneven. Different regions spin at different speeds, stretching and shearing the material like taffy. From Earth, none of this is visible. The night sky looks still calm, eternal. But in truth, the Milky Way is a living system. Every second the sun travels hundreds of kilometers, the bar turns a fraction of a degree, and unseen stars are born and die. The galaxy does not wait, it is always moving, even when we cannot see it. The Milky Way is massive, but it is not alone. Orbiting in the darkness around it is a swarm of smaller galaxies, faint companions bound by gravity. They are called satellite galaxies, and they are as much a part of the Milky Way as its arms and stars. There are more than 50 known satellite galaxies surrounding the Milky Way. Most of them are faint and fragile, ghostly collections of ancient stars drifting through the halo. But a few are bright and powerful enough to shape the galaxy itself. The two most famous are the Large Magellanic Cloud and the Small Magellanic Cloud. They are easily visible from the southern hemisphere, glowing like detached pieces of the Milky Way. Their gravity is strong enough to tug on the outer disk, sending gentle ripples through the spiral structure. Their orbits are long stretched ellipses carved over billions of years of gravitational interaction. Dozens of other companions are far smaller, tiny ultra-faint dwarf galaxies that barely hold together. Some contain just a few thousand stars. Others are wrapped in their own dark matter halos, lingering fossils from the earliest age of the universe. Many of these satellites are being ripped apart right now. As they orbit, the Milky Way's gravity peels stars from their edges, stretching them into delicate tidal streams. These glowing trails wrap around the galaxy like strands of silk, marking where a companion passed and where it is slowly being consumed. The fate of the Large Magellanic Cloud is already written. In a few billion years, it is expected to spiral inward and merge with the Milky Way, adding its stars, gas and dark matter to the growing giant. This is how galaxies evolve, not just by forming stars, but by devouring their neighbours. The Milky Way is not a quiet monarch. Its companions pull back. Their collective gravity shapes the outer disk, nudges the halo, and stirs the flow of gas in the outskirts. This is not empty space. It is a community of galaxies, each locked in a shared gravitational dance. The Milky Way may be the dominant partner, but it is surrounded by a quiet swarm of companions, orbiting together through the cosmic night. At the heart of the Milky Way, beyond the spiral arms and glowing bar of stars, lies something truly extraordinary. It does not shine, it does not move like a star. It is silent, massive and invisible, yet everything in the galaxy orbits around it. This is Sagittarius, a star, a supermassive black hole. It sits roughly 27,000 light-years from Earth in the direction of the constellation Sagittarius. From our planet, it's hidden behind thick clouds of dust and gas, completely invisible to optical telescopes. For decades, astronomers suspected that something immense lurked there, a gravitational engine powering the motions of the central stars, but suspicion became certainty through precise measurement. Near this invisible point, entire clusters of stars race around at thousands of kilometers per second. Their orbits are not random. They follow perfect curves tracing the shape of a deep unseen well. By tracking these stars over many years, scientists could weigh the object at the center. The result was astonishing. Its mass equals about 4 million times that of the Sun, all packed into a region no larger than our solar system. Nothing except a black hole can explain this. And so Sagittarius, a star, revealed itself not through light, but through its pull. Despite its monstrous size, the black hole is surprisingly quiet. It is not devouring everything around it in a blaze of energy like the raging cores of some distant galaxies. Instead, it sleeps, feeding slowly, pulling in gas and dust at a gentle pace. This is why the Milky Way's center does not blaze like a quasar. Our monster is calm for now, but this silence is deceptive. Occasionally a star or a cloud of gas wanders too close. When that happens, gravity tears it apart, heating the material to millions of degrees. For a brief moment, the quiet center ignites with X-rays and infrared light. Then the flare fades and the monster sinks back into the dark. The stars near the black hole are some of the most extreme in the galaxy. They move so fast and come so close to the event horizon that their orbits can only be explained by Einstein's theory of general relativity. Watching them is like watching gravity at its purest space itself bending under an invisible weight. Sagittarius, a star, may be hidden, but its presence shapes the entire inner galaxy. The black hole at the center of the Milky Way may be invisible, but its influence is written into the motions of everything around it. The stars closest to it move like dancers caught in a perfect orbit, their paths curved by an immense gravitational well. Astronomers have tracked these stars for decades. Among the most famous is a star named S2, which follows a long elliptical orbit around Sagittarius A star. It completes one full loop in about 16 years, reaching speeds of more than 5,000 kilometers per second at its closest approach. That is fast enough to circle Earth in less than 10 minutes. The fact that S2 and other nearby stars can orbit something so small and yet so massive is the clearest proof that a supermassive black hole is truly there. These orbits also confirm something deeper: Einstein's theory of general relativity. The stars do not follow simple Newtonian paths. Their orbits precess the point of closest approach slowly shifts, exactly as Einstein's equations predict when space itself is warped by gravity. This region of space is not just an astronomical curiosity, it is a natural laboratory for testing the most extreme laws of physics. Sagittarius, a star, may not be as violent as the cores of some other galaxies, but it still commands the inner Milky Way. Its gravity stabilizes the swirling bar of stars and the dense nuclear cluster around it. Every orbiting star, every whirling cloud of gas, every wisp of dust in the central few light years is shaped by this unseen anchor. But black holes are more than gravitational wells. They also influence their surroundings through powerful feedback. When gas falls inward, some of it is swallowed, but some is flung back out at tremendous speeds. This can heat or disperse gas around the core, regulating how quickly new stars can form there. Even a mostly quiet black hole can subtly shape the evolution of its host galaxy. Sagittarius, a star, also reveals itself through radio waves. Although it emits almost no visible light, telescopes that can see in radio and infrared wavelengths have mapped a faint flickering glow at its position. This glow comes from hot gas spiraling near the event horizon, accelerated to incredible speeds before disappearing forever. For the first time in history in the year 2022, astronomers captured a direct image of this region using the Event Horizon Telescope. The picture did not show the black hole itself. Nothing can escape from within its event horizon, but it revealed a glowing ring of light, a shadow carved into space-time. It was the face of the monster. For now, the supermassive black hole at the heart of the Milky Way is quiet, but it has not always been this way, and it will not remain quiet forever. Evidence suggests that Sagittarius A star was once more active. Astronomers have found vast bubbles of hot gas rising far above and below the galactic plane, structures stretching tens of thousands of light years into space. These Fermi bubbles, named after the telescope that discovered them, are thought to be relics of a powerful outburst millions of years ago. In that ancient moment, the black hole may have fed rapidly, unleashing jets and winds that blew across the galaxy like a storm. Even a sleeping giant can awaken. All it takes is a single massive cloud of gas, a stray star or a cluster drifting too close. When that happens, Sagittarius, a star, could flare again, lighting up the galactic center with X-rays and radio waves. A quiet monster briefly baring its fangs. Over cosmic time, the black hole will keep growing. As stars pass nearby, some will be torn apart. their material added to its invisible mass. The occasional merger with smaller black holes from disrupted star clusters will also feed its growth. It is patient a predator that hunts on a timescale of millions of years, but its influence goes far beyond what it consumes. The black hole acts as a gravitational anchor, stabilizing the central bar, shaping the orbits of stars, and helping to maintain the structure of the inner galaxy, even if it remains quiet for billions of years. Its presence will still guide the Milky Way's evolution. The ultimate fate of Sagittarius, a star, is tied to the galaxy itself. When the Andromeda Galaxy approaches and the Great Merger begins, the two supermassive black holes will spiral toward each other. They will dance a long, slow dance, losing energy through gravitational waves until they finally collide and merge into a single, even more massive black hole. The center of the new galaxy will be ruled by this colossal remnant, but that future is billions of years away. For now, Sagittarius, a star, waits in silence, a dark weight at the core of everything. It doesn't need to roar to rule. Its gravity speaks for it. The stars above us, the spiral arms, the galactic disk, they all move to the pull of an invisible heart, and at that heart, a monster sleeps. The Milky Way is not just a flat spiral of stars, it is a layered structure, a luminous disk floating inside a vast invisible sphere. This relationship between the disk and the halo shapes everything the galaxy does, how it spins, how it grows, and how it survives. The disk is the part we can see. It's a thin, glowing plane made of hundreds of billions of stars swirling gas and dark lanes of interstellar dust. Most of the galaxy's visible mass lives here. The spiral arms, the sun, the star-forming regions, all of it lies within this rotating sheet of matter, spanning more than 100,000 light-years across. It's a delicate structure, so thin compared to its width that it resembles a cosmic vinyl record spinning in the dark. Surrounding it almost like a protective shell is the dark matter halo. Unlike the disk, the halo doesn't shine. It stretches far beyond the visible edges of the galaxy, perhaps more than 300,000 light-years from center to edge. This is where most of the galaxy's mass hides. Without the halo, the disk could not spin as fast as it does. The stars on the outskirts would drift away like sparks from a dying fire. The halo isn't just empty space filled with invisible mass. It contains ancient star clusters, faint dwarf galaxies, and long tidal streams, the fossil remains of past collisions. Every one of these is moving through the halo, pulled into graceful arcs by its gravity. The halo is a quiet ocean, and the disk is the luminous surface floating above it. The relationship between these two components is a dance of forces. The disk rotates rapidly, its stars and gas locked into a flattened plane by their motion. The halo, by contrast, is mostly static, a massive spherical structure that anchors the entire system. It doesn't rotate in the same way, but its gravity gives the disk the stability it needs to survive for billions of years. This connection explains why the Milky Way can spin without tearing itself apart. The halo holds everything together, while the disk gives the galaxy its visible shape. The two are inseparable. The disk and the halo are not just separate layers stacked on top of each other. They're connected through a constant exchange of matter and energy. Every second, material flows between them, weaving the visible and the invisible into one living system. Gas from the halo slowly rains down onto the disk. It's cold, diffuse hydrogen that has drifted through space for billions of years. As gravity pulls it inward, the gas settles into the disk, feeding star formation like a slow but steady river. Without this inflow, the spiral arms would eventually run out of fuel and fade, leaving behind a galaxy of aging stars. At the same time, the disk sends matter back out into the halo. Massive stars live fast and die young. When they explode as supernovae, they eject vast amounts of gas and heavy elements into space. Some of that material escapes the disk's gravity and rises into the halo, carving giant bubbles of hot plasma that expand for thousands of light years. This creates a galactic fountain, a cycle of inflow and outflow that keeps the Milky Way chemically alive. This fountain is more than just a poetic image. It regulates the balance of gas in the galaxy. The inflow keeps star formation going, while the outflow prevents the disk from becoming unstable or choking on its own gas. It's a delicate feedback loop that has operated for billions of years. The halo also contains cosmic relics, streams of stars and debris from smaller galaxies that were torn apart long ago. As these streams fall inward, they bring not just stars but dark matter, slowly reshaping the structure of the halo itself. In this way, the halo evolves too, even if it appears silent. Meanwhile, the disk responds to every nudge from the halo. As matter flows in, the spiral arms grow brighter and denser. As it flows out, the disk ripples and shifts. The two structures are constantly adjusting to each other, locked in a slow-motion conversation that spans cosmic time. Astronomers can observe this dialogue through radio telescopes. They detect faint hydrogen signals stretching far above and below the disk, the whispers of gas moving between the galaxy's layers. Some of these flows are gentle streams. Others are turbulent rivers stirred by supernova winds and gravitational tides. This quiet exchange is one of the reasons the Milky Way has remained active for so long. Galaxies that lose this balance grow old and cold. But the Milky Way still breathes. The relationship between the disk and the halo is not a temporary phase. It is the backbone of the Milky Way's evolution. For billions of years, this quiet exchange of matter and energy has dictated the pace at which the galaxy grows, shines, and changes. The halo acts as a gravitational skeleton. It defines the scale of the galaxy and provides the deep well of gravity that holds the disk together. Without the halo, the disk would not be stable. It would warp and tear apart under its own rotation. The invisible mass around the Milky Way is what gives it structure and strength. The disk in turn gives the galaxy its luminous identity. It's the part that forms stars, glows with starlight, and creates the spiral arms that define the Milky Way's shape. Every change in the disk, every burst of star formation, every ripple of turbulence, every wave of supernova explosions echoes outward into the halo. The galaxy is not a set of isolated parts. It is a single living system. This feedback loop also sets the lifetime of star formation. As long as the halo continues to feed cold gas to the disk, new stars can keep forming. But if the halo's reservoir runs dry, the galaxy will slowly grow quiet. The spiral arms will fade, the disk will cool, and the Milky Way will drift into a quieter, redder future. The halo also stores history. Every merger with a smaller galaxy leaves behind new streams, new pockets of dark matter, new structures folded into its depths. The disk may be vibrant and ever-changing, but the halo is the archive, the memory of every encounter and collision. Over cosmic time, this interplay has shaped not just the Milky Way structure, but its destiny. When the Great Merger with Andromeda Galaxy finally arrives, the halos of both galaxies will collide long before their disks touch. The invisible skeletons will merge first, laying the gravitational foundation for the creation of an entirely new galaxy. The disk and the halo may look like opposites, light and dark, thin and wide, visible and hidden, but they are bound together. Their relationship is what allows the Milky Way to live, grow and evolve over billions of years. Every star that shines in the night sky owes its existence to this silent partnership. The Milky Way is not drifting through space alone. It belongs to a cosmic neighborhood, a loose association of galaxies held together by gravity. This neighborhood is called the local group. It is our corner of the universe, a quiet cluster of galaxies orbiting and interacting in a shared gravitational field. The local group contains more than 80 galaxies, though most are faint dwarf galaxies that orbit the larger members. At its heart are three major players: Milky Way, Andromeda Galaxy and Triangulum Galaxy. These three galaxies dominate the group's mass. while dozens of smaller companions swirl around them like fireflies around bonfires. The entire local group spans more than 10 million light-years from end to end. Within this space, gravity gently binds its members together, though the distances between galaxies are vast and silent. Each galaxy moves on its own path, but they all share a common future. The Milky Way and Andromeda are by far the largest. They sit only about 2.5 million light-years apart, close enough on cosmic scales to feel each other's pull. Their mutual gravity is slowly drawing them together, setting the stage for a colossal merger in the far future. The local group is not a dense cluster. Unlike the crowded blazing cores of rich galaxy clusters, our neighbourhood is relatively quiet. Most of its galaxies are small isolated dwarfs with weak gravitational pulls. Some orbit the Milky Way, some orbit Andromeda, and some drift alone in the dark like wanderers on the edge of a great plain. Despite its calm appearance, the local group is full of motion. Every galaxy is moving, orbiting, drifting, being drawn by invisible threads of gravity. The Milky Way itself is on a slow, inexorable path toward Andromeda, and everything within the group will eventually be swept into this future collision. For astronomers, the local group is more than just home. It is a laboratory. Because these galaxies are close, we can study them in detail. Their stars, their gas, their structure, their histories. They reveal how galaxies live and evolve not in isolation, but as part of a larger connected system. The Milky Way may feel immense, but it is only one voice in the quiet chorus of the local group. The galaxies of the local group are bound together by a shared gravitational field. Even across millions of light-years, their invisible pulls connect them like threads in a vast silent web. The Milky Way and Andromeda galaxy dominate this web, together containing more than 90% of the group's total mass. The pull between these two giants is not weak. They are moving toward each other at a speed of about 110 kilometers per second. Though that may sound fast in cosmic terms, it is a slow, inevitable drift, a motion that will bring them together in roughly 4 billion years. This isn't a collision in the explosive sense we imagine with solid objects. Galaxies are mostly empty space. When they meet, stars will pass by stars, and the structures will merge in a slow gravitational ballet. Orbiting these two giants are dozens of dwarf galaxies, each one a faint island of ancient stars. Many of them are satellites of the Milky Way. Others belong to Andromeda. A few drift in between following elongated orbits that span millions of light-years. Their movements trace out the gravitational shape of the local group, like sparks outlining an invisible fire. Triangulum Galaxy. The third largest member is much smaller but still plays a role. It orbits Andromeda and may eventually join the Grand Merger as well, adding its stars to the future combined system. Even the tiniest dwarf galaxies, though fragile, contribute to this web of mass and motion. The local group is also moving through space as a whole. It is being drawn toward a distant region called the Great Attractor, a gravitational anomaly far beyond our neighbourhood. The entire group Milky Way Andromeda and all their companions is drifting through the cosmic web at hundreds of kilometers per second, a fleet of galaxies sailing together through deep space. Although the local group is small compared to massive galaxy clusters, it has a well-defined gravitational boundary. Beyond this point, other galaxies are no longer gravitationally bound to it, and instead follow the expansion of the universe. Inside this boundary, everything shares the same fate. The Milky Way's place in this system is not static. Its orbit, its satellites, and its future are all shaped by the gravitational landscape of the local group. We are part of something larger, a community of galaxies tied together by gravity and time. The local group is just one small cluster in a vast cosmic landscape. It floats like a single island in an ocean of galaxies, connected to others by thin filaments of dark matter and rivers of gas. To understand the Milky Way's future, we must see not only its neighbours, but also the larger structure it belongs to. The local group is part of a massive region called the Laniakea Supercluster, a gravitational basin containing tens of thousands of galaxies. Within this structure, entire galaxy groups flow together like streams feeding a cosmic river, and the local group is one of those streams drifting toward a distant gravitational center. This larger structure is mapped not by light, but by the motion of galaxies. Astronomers track how groups like ours move through space, revealing patterns shaped by dark matter on colossal scales. The local group is not fixed. It is slowly falling toward the great attractor, a mysterious region of enhanced gravity hundreds of millions of light years away. Compared to the enormous clusters at the heart of the supercluster, the local group is quiet and modest. We do not live in a dense, turbulent galaxy cluster, where collisions happen constantly and galaxies burn bright with rapid star formation. We live in the cosmic suburbs, a calm, stable neighbourhood on the edge of something far larger. This quiet position has shaped the Milky Way's entire history. Because it is not trapped in a violent cluster core, it has been able to maintain its disk structure for billions of years, forming stars at a steady pace rather than burning out in a single blaze. Our galaxy owes its spiral arms, its stability, and even the existence of its habitable zones to this peaceful location in the cosmic web. But even in this quiet corner, the local group is not immune to destiny. Over billions of years, it will likely merge with other nearby groups, forming a larger structure, perhaps a small cluster of its own. Eventually, these structures may drift together under the pull of dark matter, their shapes stretched and folded into something new. From a human perspective, this is unimaginable time, but for the universe, it is simply the next step. The local group is not permanent. It is a chapter in a much larger story. The story of cosmic structure growing, collapsing, and merging over eons. The Milky Way, Andromeda, and all their companions are part of this vast choreography. We are not just residents of a galaxy, but participants in the slow, majestic dance of the cosmic web. In the stillness of the night sky, Andromeda Galaxy looks calm, a faint misty patch of light barely visible to the naked eye. But behind that calm appearance is motion. It is not drifting away like most galaxies in the expanding universe. It is moving toward us. The distance between Andromeda and Milky Way is about 2.5 million light-years. That seems impossibly far, but their mutual gravity is strong enough to overcome the expansion of space between them. Andromeda is on a collision course closing in at roughly 110 kilometers per second. This is not a guess. Astronomers have measured it with precision. Using space telescopes, scientists tracked tiny shifts in Andromeda's light. The Doppler effect, the same principle that makes a passing siren change pitch. That shift reveals not only how fast Andromeda is approaching, but also the direction of its motion through space. Over years of careful measurement, the evidence became undeniable. The two great spirals are moving straight toward each other. Unlike many galaxy encounters, this one will not be a glancing touch. It will be a head-on collision, a slow but unstoppable embrace shaped by gravity itself. The estimated time of impact, about 4 billion years from now, on cosmic timescales, that is soon. But calling it a collision is misleading. Galaxies are made mostly of empty space. When they meet, their stars will not crash into each other like cars on a highway. Instead, they will pass through almost entirely unscathed. The real drama will happen on the grand scale. The shapes of both galaxies will stretch, twist, and tear. Their stars flung into new orbits like dancers in a slow-motion storm. The supermassive black holes at their centres, Sagittarius a star in the Milky Way, and Andromeda's central black hole will also begin their own long spiral, a dance that will end in one of the most powerful mergers in cosmic history. We live in the quiet before a storm we will never witness. The collision will not be sudden, it will unfold over billions of years, a slow-motion transformation on a scale almost too vast to imagine. The first encounter will happen when the outer halos of the two galaxies touch. This will occur long before the visible disks collide. The halos, vast spheres of dark matter stretching hundreds of thousands of light years, will begin to overlap, locking the galaxies into a single gravitational system. From that moment on, their fates will be bound. As the galaxies draw closer, tidal forces will twist their shapes. The elegant spiral arms of both galaxies will stretch like taffy, creating long tidal tails that arc into intergalactic space. Stars will be pulled from their original orbits and launched on wild trajectories, some flung far into the outskirts, others sent plunging toward the centers. Eventually the disks will pass through each other. To an observer watching from a distant galaxy, it will look like a grand ballet, two luminous whirlpools merging in slow spirals. Despite the chaos, almost no stars will collide directly. The distance between stars is simply too vast, but their orbits will be rearranged. The familiar spiral shape of the Milky Way will be gone, replaced by distorted streams and glowing arcs of scattered stars. During this time, massive bursts of star formation may ignite. Gas clouds that were once drifting peacefully will slam into each other, triggering waves of stellar birth across both galaxies. The night skies of any inhabited worlds would be filled with breathtaking vistas, sheets of light, vast streams of stars, and brilliant new clusters blazing into life. After the first pass, the galaxies will drift apart slightly, still tethered by gravity, but they will not escape each other. Their mutual pull will reel them back in. They will fall together again, each pass drawing them closer, each encounter shredding their structure further. Through these cycles, the Milky Way and Andromeda will stop being two galaxies. They will become one, a swirling chaotic structure in the process of rebirth. At the heart of this slow collision, their central black holes will begin their own gravitational dance, spiraling closer with each orbit, shaping the future core of the new galaxy. This is not the end of the Milky Way. It is its transformation. After billions of years of slow gravitational choreography, the two galaxies will finally settle into a single structure. The spirals that once defined the Milky Way and Andromeda will be gone, their elegant arms erased by tides and time. What remains will be a new galaxy, larger, rounder, and brighter than either of its parents. Astronomers already have a name for this future system, Milky Way. It will likely resemble a giant elliptical galaxy, a smooth glowing sphere of stars with little trace of its spiral origins. The new galaxy will contain nearly 1 trillion stars, drawn from both systems and from the tidal streams cast into intergalactic space. The central region will be dominated by a single supermassive black hole, the product of the merger between Sagittarius A and Andromeda's black hole. Over millions of years, the two black holes will spiral toward each other, radiating gravitational waves into the cosmos. Their final collision will release an enormous burst of energy, a ripple through space-time that will travel across the universe. This merged black hole will anchor the new galaxy. Its gravity will shape the stellar distribution, stabilizing the heart of Milky Way just as Sagittarius, a star, once anchored the Milky Way. For any surviving stars, their orbits will be entirely different. Many will have been thrown into elongated paths far from the center. Others will settle into new stable orbits in the remnant core. The familiar constellations we know today will be erased long before the merger is complete. A night sky seen from Earth, if Earth still exists, would be unrecognizable. Star formation in Milky Way will eventually slow down. Much of the gas will have been consumed or blown away during the collision. Over time, the galaxy will age and redden, its young hot stars fading as new ones are born less frequently. It will enter a quieter phase of cosmic life, a grand glowing giant drifting through the dark. But this is not destruction. It is transformation on a scale beyond anything we can imagine. The Milky Way story will not end in fire. It will live on in a new form. Its stars, its black hole, its legacy woven into a new cosmic structure. billions of years from now, the local group will be reduced to a single massive galaxy, and in the deep silence of space, Milky Way will continue to shine. For billions of years, the Milky Way has drifted through the universe like a vast luminous river. It has no single beginning that we can witness, and no fixed shape that will last forever. It is alive not in the way a creature lives, but in the way a system breathes. Its stars are born in the cool darkness of spiral arms, live brilliant lives and die in explosions that feed the next generation. Its spiral pattern slowly rotates. Its bar turns through the core. Its halo holds everything in place. Every motion, every orbit, every glowing star is part of a larger rhythm. The Milky Way is not a frozen image in space. It is a process. The disk grows and shifts. The halo absorbs ancient streams, and the galaxy evolves. Its spiral arms are not static lines of stars. They are waves of density flowing through the disk like music through air. What we see in the night sky is a single frame in a film billions of years long, and we are part of it. Our star is just one among hundreds of billions, riding quietly through the Orion Arm. The entire history of humanity, every story, every dream, has unfolded during a tiny fraction of one orbit around the galactic center. We are travelers aboard a moving world, on a journey we can neither steer nor stop. Yet despite its constant motion, the Milky Way has given us stability. Its calm position in local group, its balanced structure, and its steady pace of star formation have made it a cosmic cradle. For billions of years it has quietly turned, building the conditions that made life possible. But nothing in the universe is permanent. Galaxies collide, merge, evolve. The Milky Way itself is heading toward a grand transformation. Its spiral arms will fade, its stars will be scattered into new orbits, its core will be reborn in a new form. It will not vanish, it will change. The Milky Way has existed for more than 13 billion years. Before our star was born, before Earth formed, before life even existed, the galaxy was already spinning in the dark. Countless generations of stars have lived and died here, each one adding its light, its elements, its story to the whole. We arrived late. Our solar system joined the galactic dance less than 5 billion years ago, a newcomer in a story already ancient. And yet in this brief moment, we have gained the ability to look outward and glimpse the structure that cradles us. When we look up at the night sky, we do not just see stars, we see the disk we are inside of. The faint band of light arching overhead is the cross-section of our galaxy. Billions of suns woven together into a single glowing river. We are looking along the spiral arms, through dust and starlight, across unimaginable distances, but this view is temporary. The Milky Way we know is not eternal. Its arms will one day be torn and reshaped. Its stars will scatter into a new configuration. Its name itself may fade, but its essence, the matter, the energy, the gravity that built it will endure in a new form. This is the nature of galaxies. They do not end, they transform, and yet the fact that we exist here, in this tiny window of time, able to understand even a fraction of this vast story, is extraordinary. We are not the center of the galaxy, we are not its purpose, but we are its witnesses. Our world moves with it, our star orbits its heart. We live inside something far larger than ourselves, a living galaxy in a living universe. And when we look up into the night sky, we are not just seeing stars, we are seeing home.